Good morning, everyone.
Good morning, Kurosh.
Hi. How are you?
Good, and you?
Doing all right, thank you.
Morning,
I think we should wait. Good morning. Good morning. I think we should wait a few minutes, maybe, so some people can join, and then we can get started. Yeah.
Kurosh, do you see my screen right now? Or?
Yeah. Do you want to make it full screen?
Yes.
So one day you're gonna have to tell me where I can get me one of those cakes.
Well, everything is closed these days. you may have to go all the way to Switzerland.
That's not such a bad idea.
It is a really tempting piece of cake.
Oh yeah.
In Seattle, you guys have great pastry. No, Jeff?
We do. Yeah, we do. I've got I've got two little places, a donut shop, but then also a pastry shop that are right around the corner from my house. It's
sounds dangerous.
It's challenging. It's very dangerous. We have a once a month. Once a month. That's it.
Actually, the view behind Michael Grilliot. Is it Seattle? It's beautiful.
Thanks. No, it's not Seattle. It's actually British Columbia.
I see.
Central Coast. That's where I did my PhD research. It was gorgeous.
Yeah. So we are still waiting a few minutes to let a few more participants to join. So enjoy your coffee in the meantime. All right, so I think let's get started. Good morning, everyone. My name is Joël Conte. I'm the PI of the NHERI experimental facility at the University of California, San Diego. I want to welcome you for the second day of our workshop. Let me try to. Second day of our NHERI workshop jointly with the Rapid NHERI facility at the University of Washington. So just a few words about what we did yesterday. For those of you who could not attend the day yesterday, you can see the agenda for day one. we focused on describing the capabilities of the two facilities and gave best practices for proposal preparation. And the agenda for today, we are going to, the theme for the day is new features, new technologies, cross-pollination between our two NHERI experimental facilities. We will start with a virtual tour of the facilities to give you a taste of how it would feel if you were here in person. So we start with the construction of the LH Post 6. As I mentioned yesterday, the upgrade to 6 degrees of freedom is underway. So it's a construction site right now. And then a virtual tour of the RAPID facility. Then we will have a talk on new capabilities, new technologies by Professor Gilberto Mosqueda and Tara Hutchinson from UC San Diego. Then we will have the RAPID equipment and example of large-scale experiment, Professor Jeffrey Berman from the University of Washington. Then we were scheduled to have Dr. Joy Poshki from the National Science Foundation to give a presentation at 9:50. I made a mistake. I didn't confirm the meeting. I confirmed it too late with her calendar filled up. So she is willing to accommodate us and give the presentation during office hours at 1:30 this afternoon. We will take a poll at that time at 9:50 to see how many of you are interested in that presentation. And if there are enough, then she will give it. Otherwise, she mentioned that you could contact her directly. So let's wait for the poll at 9:50. Then we'll have a coffee break, question and answers, coffee break. Then Dr. Kurosh Lotfizadeh from UC San Diego will present an example project and followed by an example project from the RAPID by Professor Paolo Calvi, University of Washington. And then we will have a panelist presentation and open discussion focusing on, the future, new application, new technologies, new projects. And then we'll have some concluding remark by myself and Professor Joseph Wortman, who is the PI of the RAPID facility. And we will also this afternoon have office hours to answer specific question that you may have about your proposal or your project. So, Kurosh, do we have any logistic to talk about?
Well, the survey is something that we should bring up right now.
Okay. And when we organize this workshop, we are asked by the National Science Foundation to run a survey and to present the results in our reports to the National Science Foundation. This survey also allows us to evaluate ourselves, of course, and to improve our future delivery of the workshops. So we'll be very grateful if you can take the time to fill the survey. We'll give more information at 10 o'clock on where to take it, or maybe Kurosh, you can already tell them where they can take the survey online.
Yeah, of course. So the survey is done through a Google form. It's very simple to use. It's incredibly intuitive. You don't need a login or anything. And all the survey results are anonymous. So please feel free to speak your mind. I will send an email out after the workshop and I'll include the link to access that survey. And we'd greatly appreciate it if you can give us your feedback. That'll help us a lot in the future.
Thank you, Kurosh. So I think now we can get going with the virtual tour of the construction of the LH Post 6. We call it LH Post 6 now to differentiate it from the LH Post that had only 1 degree of freedom. And Kurosh, I think you will play that one.
Yes. Sorry, I'm going to start sharing here.
Yep.
Hello, I am Joël Conte, Professor of Structural Engineering at UC San Diego and in charge of the upgrade of our large outdoor shake table. So I would like to give you a tour of the upgrade, construction side of the upgrade. and focus on some important points. So let's go. So here we are at the Engelkirk Structural Engineering Center. We are arriving. We are pointing west. You can see here a large tent. We had to build these tents to store a lot of equipment, several hydraulic equipment mainly, since the upgrade is taking quite some time. It started, the project of the upgrade started on October 1st, 2018 and will end in late spring, summer 2021. Here you see the safety towers that we use when we are testing some specimen to prevent them from collapsing. All right, and here we are turning towards our staging slab. We had a second tent earlier here on that slab as well, but now you can see these two big packages that contains actually the two new horizontal actuators. Now we are walking back towards the shake table, and you start to see the platen of the shake table that is resting on four large reinforced concrete columns that were built just for the temporary storage of the platen. The platen weighs about 145 tons, and it will require some work. We require some drilling of many holes to install the new wear plates underneath, and we have to do some machining on the underside of the platen to provide ideal surfaces to slide over the vertical actuators. And as we turn south, you can see the hydraulic power building. It's the same building that we had the last 15 years. It contains all the hydraulic power supply and the controller of the table. So we are going to have an overall look at the inside the reaction map. So you see a number of things here, a lot of piping, and the red pipes is the one that will have the pressure, the main pressure pipes. The red pipes, if you follow them, they follow a ring. We call this the main pressure ring. And the blue pipe are the return pipes. When the shake table will be working, the fluid inside the red pipe will be at 3000 psi. Inside the blue pipe, the return will be probably below 100 psi. You see, these are gigantic pipes. They have a 12-inch diameter inside diameter. They are 1¼ inch thick. You also see a lot of smaller pipes. The smaller pipes you see red, blue, and yellow. So these are the pilot. The red and the blue are the pilot pressure red, pilot return blue, and the yellow one are the drain pipes. I'd like you to observe, these two walls that each of them support 3 vertical actuators. You see the steel base plate that will support the actuators. You notice that the plate that are at the end of each of the wall, so 4 of these plates, they had to be extended because in the 6-degree freedom upgrade, the 4 corner vertical actuators have to be moved in by 10 inch to accommodate the new kinematic capabilities of the platen. So here you see the platen. You see these 2 large steel plates that will receive the head of the horizontal actuators. In the 1-degree of freedom configuration, they used to be fixed here. And now in the 6-degree of freedom configuration, there will be 1 horizontal actuators fixed here and the other one connected here. We are going to go under the platen to show you surfaces over which the vertical actuator will slide, the top of the vertical actuator. So you see these surfaces, they They had rusted. In the last 15 years, we just grit blasted these areas. And you see the one in the middle here. So there is 3 on each side. We are going to install some very large wear plates, half-inch thick wear plates, highly polished, and we will have to maintain a planarity of plus or minus 24 thousandths of an inch of each of these 6 areas. Now under the platen here, you can see 2 very large, the 2 large saddle blocks that will allow to anchor the top of the hold down strut. Right? And we will have a new one in the middle. You can see that the one in the middle has never been used, in yellow here. And then at the other end of the platen there is the existing one. So we will have 3 hold down strut to keep a very large overturning moment capacity. Here I would like to show you the northwest corner of the reaction mass of the shake table. You can see here that we are in the process of post-tensioning the large steel plate that serve as a base for the horizontal actuators that I'll show you in a second inside the reaction mass. But you can see here 6 post-tensioning rods with the nuts and the plates, washers. And you also see that we have grouted the volume behind the plates, between the plates and the reaction wall. And now we're going to go and look at these large steel plates that are inside the reaction mass. So you see one of them here that has been positioned. It has, now what needs to happen is we need to do some surveying work to have all the accuracy in the final positioning and then grout the spacing between these plates and the reaction mass. And we have 4 of those because now we're going to have 4 horizontal actuators. You can see the location of the other 2 that we will work on very soon. And now we are going to go inside the building, see a number of things. We are going to look at, we have 2 new pumps to supplement the existing 2-1. And we're going to look at the new accumulator bank that is completely installed and a lot of the new piping inside the building. So let's go. All right, so here we are turning around the west-south corner of the hydraulic power building. And you will see the 2 new pumps, brand new pumps that are being added to the existing two pumps. And you can see that we had to, of course, connect them to the cooling system. We have a new cooling tower. You see the brown pipes there for the cooling system, and also bring the electrical power here. And now we are going to see next to this the brand new accumulator bank, very large accumulator bank, 75 bottles with a total volume of 10,000 gallons. So here you see they are in a group of 5 bottles. So we have 15 of these sub-modules. You can see that every bottle is monitored for the pressure with wireless pressure sensors. And this is basically these 2 pumps that you have seen. They are going to be used to mainly pressurize the accumulator bank, to push some oil at the base of each of the bottom, below the piston, until the nitrogen pressure, which is above the piston, reaches a pressure of 5,000 psi. In idle conditions, the pressure of the nitrogen in the bottle is 3,000 psi. So about 20-25% of the bottom of each bottle will be filled by oil. And that pressurized oil is the one that is used to control the horizontal and vertical actuators when we reproduce a multi-dimensional earthquake ground motion. And here below the catwalk, you can see clearly some red pipes. So the pressurized oil that is inside the accumulator bank is released through some blowdown valve, released into these red pipes, pressure pipes, that connect to the one that we have seen inside the reaction mass. And you also see here the blue pipes, and that's the return pipe, and you can see that they return the fluid at low pressure all the way to the surge tank. You see this large surge tank, we did not have to change it. We had sized it properly 15 years ago, thinking about the upgrade. All right, so now let's go and look at the cooling tower. We had to completely replace the old cooling tower that was close to the end of its life. Number one, and number two, didn't have the cooling power required for the upgraded shake table. So behind me, you see the cooling tower for the 4 powerful pumps that we have in the system. You see a lot of circuitry here, a lot of pipe for the water, and the electrical system support the cooling tower. Look at the size of the cooling tower compared to the building. It's pretty appreciable. We're going to go on the other side now. So here you see the 2 blue tanks here. Contains chemical that prevent calcification inside the heat exchangers of the pumps. This is a problem that we experienced in the past, and we don't want this to happen in the future again. So let's go inside the building. So here we have a very good view of, first, you see the 2 existing pumps. So one of them is going to continue to serve as the pump that is feeding all the pilot flows to control the spool of the servo valves. And the second pump will be also used to pressurize the accumulator bank. So we will have 3 pumps to pressurize the accumulator bank now. You see the top of the accumulator bank. Again, these modules of 5 bottles each, 15 modules, 75 bottles. You can see again the surge tank here. It's a 20,000 liter surge tank. So now we are going to go downstairs and go all the way to the bottom of the building to appreciate the size of the accumulator bank from their footing and the surge tank, and also follow the path of the oil from the accumulator bank all the way to the reaction mass. So now here you see the incredible height of this new accumulator bank, and again the surge tank from below. And you see the 2 pressure pipes. Most of these pressure pipes were prefabricated by GS Hydro in Houston. One link that had to be welded in the side here is the one that I'm showing you here. So you see these 1, 2, 3, and 4 big weld, circular weld. Same thing for the second pipe in the back. These took a long time, and they had to be x-rayed as all the other weld. And these are, again, huge pipe, 12-inch diameter inside, 1 1/4 inch thickness. So you see, again, there they are coming out of between the 2 accumulator banks here, which release the oil through some blowdown valve that we can see here in the view of the camera. With the 1 degree of freedom configuration, we used to have only one of these pressure pipes, and we had to double it. So now we are going to enter the tunnel. And you can see below these two red pipes, there are also two blue pipes that are the return pipes. You see that the tunnel is now occupied hugely by these large pipes. Now we are entering the reaction mass. You can see here the joint of the foundation of the building and the reaction mass. So we're on the south side of the reaction mass with a tunnel that brings the one pressure pipe and one return pipe towards the east, and then on the other side towards the west. And now we are inside the reaction mass. We have seen it a few minutes ago from above. So now you can see the big wall, the large wall here that is supporting 3 of the vertical actuators. You can also see the steel base plate that will support the vertical actuators. As I explained earlier, 4 of them had to be extended. You can see the extension here with rebars welded to the plate and anchored down to the concrete. We still need to grout this. We had to do this because the vertical actuator now in their new position will be 10-inch more on the inside than before to accommodate the kinematic capabilities of the platen with the new horizontal actuators. You can see here many of these large blocks called hydraulic manifolds. And at the bottom again, you can see now closer than before, again the red and the blue pipes, but you can see these large blocks with 3, 4, 5, 6, 8, 16. Each of them has 16 orifices, and these will allow flexible hose to bring the high pressure fluids to the servo valve of the horizontal actuators and get the return. And you can see here again from very close one of the gigantic steel plate to which the horizontal actuator will be anchored. So the swivel base of the new horizontal actuator will be bolted to these two plates protruding out that you can see here. This plate has not been grouted yet. Very shortly, in the next week or so, we will grout them against the reaction mass after a very accurate positioning. I'd like to bring to your attention, you see this opening into the reaction mass. First of all, the tunnel through which we came, and then you have the door on the west here, the door on the north, and the other door towards the east. This reaction mass has tunnel inside. It's not a solid block of concrete. Also, would like to show you this middle area between the 2 large walls supporting the vertical actuators. You can see these catwalks, and so we are going to replace the 2 hold-down strut that were here in the last 15 years. You can see here on the video the saddle, one of the 2 saddles that is anchoring the base of the hold-down strut to the bottom of the reaction mass. We will need to bring a 3rd hold-down strut that has already arrived. You can see it here. Under the blue tarps, we have the 2 existing hold-down strut, and under the brown tarp, we have the brand new one that has arrived on site a few months ago. And now that 3rd one will be anchored down in the same way as the other 2 in the middle to increase the overturning capacity of the shake table platen. So this concludes our virtual tour of the construction site of the upgrade of the LH post to 6 degrees of freedom. We will call the facility the LH post 6. We are right now on course to reopen the facility in July 2021. Very sorry that you could not be here in person. It would have been nicer. We hope that you will have a chance to come soon, before it reopens or soon after it reopens. Thank you very much for your attention.
Okay, great. So hopefully it gave you a feel of the construction site. It's a little bit outdated. At this point, we have now grouted the 4 big steel plates, interfacing the horizontal actuator to the platen. And we are in the process now of bringing back of installing the 2 new horizontal actuators, back inside the reaction mass. I think I mentioned somewhere that we will reopen in July, if I remember correctly. This has changed also. We experienced some setback. To make a long story short, the 2 existing horizontal actuator, their swivel, the front swivel, was found to be internally very rusted over the last 15 years and could not be reused after the upgrade. This was a big surprise. MTS, with whom we are working on this upgrade, had to restart the manufacturing of 2 new swivel, and the lead time was 7 months. It was discovered late, so we are doing everything we can to minimize the delay. But now, because of that, the opening is scheduled early October. So I think we will now go to the next presentation, which is the virtual tour of the RAPID facility. Kurosh, will you play it, or is it somebody from your team?
Jeff will.
Jeff?
Yeah, I think Jack is going to play it.
Okay, great.
Hi, and welcome to the RAPID facility. I'm Joe Wortman. I direct the Natural Hazards Reconnaissance Facility, or the RAPID as it's known. We're going to take you for a quick tour of the facility today. We are based here at the University of Washington, and we're a partnership between the Oregon State University, Virginia Tech, and the University of Florida. So come inside, you'll meet some of our staff, and we'll show you the facility. This is Moore Hall, the civil engineering complex at the University of Washington. We're going to step into our main office, and when we're out of the time of COVID, you'll all be welcome to come and use our post-processing facilities. We have some downstairs that you're going to see as well. The mission of our facility is to support investigators in natural hazards reconnaissance investigations. We provide equipment, expertise, and software services to help you reach your reconnaissance goals and support your natural hazards field missions. And now I'm going to hand it over to our staff.
Thanks, Joe. Hi, I'm Jacqueline Peltier, Operations Specialist here at the RAPID. I also go by Jack, and sort of a jack of all trades here at the facility. I am responsible for various business, communications, and outreach activities, and also oversee some of our equipment organization, training, and procurement. As with all our staff here at the facility, you'll sometimes see me out on deployment collecting your perishable data. Here are our staff's office workstations where we do our day-to-day tasks. In non-pandemic times, this is where we'd be answering your email questions and requests, following up with you on our facility and design safe Slack channels, and managing some of your data backup and processing. A couple of the workstations are open for your researcher and student use. This is the conference section of our office. You might recognize this area if you've had meetings with us in the past. This is where our team comes together to discuss operations and where we hold virtual meetings and conduct small workshops, like the Data Processing Intensive Workshop we held last winter. This is also where we first receive and check in your equipment when it's shipped back from a project deployment. Next, Let's go downstairs and meet up with Andrew Lyda and the rest of the Rapid headquarters space.
Hi there, I'm Andrew Lyda, an operations engineer with the Rapid facility. I assist the operations manager and specialist, Mike and Jack, with whatever they need and specialize in many of the technical roles here at the facility. So that includes running and maintaining the equipment you'll see in the next two rooms, as well as processing and handling data on the machines in this room. Welcome to the Rapid facility, computer lab affectionately known as the holodeck. The computer lab serves as a primary data handling and sharing center for the Rapid facility. We handle any data collected on facility equipment here. Data is backed up to servers, so nothing is lost, and if you require processing, we have 3 top-of-the-line workstations on your right. Each of these is loaded with state-of-the-art software key to processing much of the data we collect. We can process the data, or you can use one of these machines to process too. This is also a sharing space. The room is built for facility users and students to have a space to interact. Here you can see our group collaboration area for presentations, mission notes, planning meetings, and anything else you'd like. On the other side of the room here, we have set up mobile workstations for researchers or students to use as their own desk here at the Rapid. Bring a laptop with you or check out a facility laptop and work from your own desk. Computer screens are supplied along with direct internet connections and access to Rapid staff. If you would like to test or train on a piece of equipment, you can also set up at a desk here and we'll bring out a piece of equipment. As an example, we brought out the Leica RTC 360 here. It is great for quick, indoor, and close-range LiDAR scanning. You can practice scans and then load the results into a laptop to practice processing at our workstations. Here, you can see a dataset collected by the RTC 360. This was processed using Leica Register 360, licensed to the Rapid facility. The product is being used to build a 3D model of a shake table test. And so that is the Rapid Facility Computer Lab. Start training for your project here, work with your team, and then process your data after deployment, all with the Rapid facility. To get that data though, you'll need the state-of-the-art equipment housed at the Rapid facility. Peek further behind our doors, Dr. Jeff Berman will show you around our equipment hangar, or what we call the shuttle bay. Jeff?
Hi, I'm Jeff Berman. I'm the Rapid's operations director and a professor here in structural engineering in the civil engineering department at the University of Washington. And I get the pleasure of showing you into our equipment storage area, also known as the shuttle bay. So come on down. This was used to be an old geotechnical lab facility that we repurposed into our equipment storage area. And as you can see, it's super well organized. We'll walk through a little bit what's on the shelves in a minute. But super well organized, very easy for us to find stuff and ship it out to you. As you can see, everything's packaged well in Pelican cases, and that's how you'll receive equipment from us. Everything pretty much ready to go. To give you an idea of what's in a box, what's in a Pelican case when you receive it from the Rapid facility, here's our applied street view system. It gets mounted on a car, works just like any other street view system, collects 360 degree images as you drive around. And so when you receive a case from the Rapid, this is what it's going to look like. Everything's going to be labeled, well marked. There's going to be instructions inside the box. These instructions, of course, are also available on our website in PDF format so that you can look at them on the plane as you're going on a deployment. But everything's kind of there, how to use the equipment, and even instructions on how to package it, how to repackage the Pelican case to get it back to us. Sometimes, of course, packing the Pelican cases can be a little complicated. And so again, everything's labeled, and how it's put together will be obvious with the instructions. And so you can see, you know, custom pieces, custom foam pieces. Every Pelican case is situated to fit the piece of equipment that's in it. And then, of course, each case is well marked and well labeled. You know that it's one of ours, and it should come back to us. There we go. Also, as we look at the equipment storage shelves, you know, they're really well organized. We've got a range of UAS systems, you know, UAS systems for short flights, UAS systems for long flights, heavy payloads, high winds, a little bit of rain even. We've got geotechnical systems, including our seismometers, MASW system, site characterization systems. We've got our survey equipment, including a robotic total station, GNSS receivers, street view system, a range of LiDAR equipment that's ready to go, including lightweight LiDAR systems that are great for doing interiors of buildings, very easy to set up, gather a lot of data. This is the RTC 360. Really interesting. It comes kind of ready to go, its own backpack, its own tripod, everything put together in a real nice package. And then we've got our longer range LiDAR systems down here, the MapTech systems, good for up to a couple kilometers for collecting perhaps landslide information, things like that. We've got our coastal section over here, including components for our Z-boat, which is actually stored in another room, and water level gauges, things like that. And of course, we have our wrap packs as well, which have your traditional kind of reconnaissance equipment that you might have used in the past, things that you need in the field like tape measures and plumb bobs and distance disto gauges and things like that. So that's our equipment storage room. We obviously spend a lot of time keeping ourselves organized and making it easy for you when you grab our equipment and when it comes to you. So thanks for joining me, and we'll send you up to the Rapid workshop space next.
Hi everyone, I'm Dr. Michael Grillo. I am the operations manager here at the Rapid facility. I'm typically your first contact when requesting to use the facility. I interface with facility users from start to finish on their projects. From project proposal development to research design, field planning and implementation, and data archiving, I'll be there to help make your deployment a success. The room we're going to show you next is the Rapid Workshop. This is a dual-purpose room used for storage of some of the larger pieces of equipment, as well as a fully outfitted workshop. This gives us the space to perform servicing and maintenance on equipment, prepare for deployments, and receive and clean equipment after each deployment. This is the primary staging area for equipment when a deployment starts. This is where we come to pull out all of the equipment, update it as needed, clean it, and bench test it before sending it out. Going around the room, here we have a 3D printer that we have used in the past for printing scale models of field locations for visualization and outreach. We also use this to print custom parts so we can modify equipment for specific uses. Here we have the Rapid server. Coming back from a deployment, all of the data is compiled onto our server before being transferred to your DesignSafe project. Part of the room is used for storage of field gear, safety and survey equipment. We have safe battery storage for all of your equipment batteries, the Z-Boat, our single beam echo sounder, and Mini Ranger, the drone-based LiDAR system, also known as an uncrewed LiDAR system, or ULS, are stored in this room. We also have a small kayak for Z-Boat deployments that we can use as a backup in case the Z-Boat gets stuck. We have 3 equipment workbenches available to test and work on equipment before and after deployments. We keep all of our shipping and packing materials in here so we can appropriately pack for each piece of equipment. We work with a lot of high precision equipment that requires special handling, so we want to make sure that the equipment reaches you safely and in working order. Now that we're all packed up, we're ready to go.
Hi, I'm Sean Young. I'm a part-time staff member of the Rapid facility. Now that this equipment is packed, we can ship it to you directly or join you in the field. Either way, this is ready to collect your high-precision, perishable natural hazard data.
This is Dr. Grillo again. On behalf of our leadership team and staff at the Rapid facility, we thank you for visiting us. And now we are ready to go on your deployment.
Thank you very much, University of Washington, for your excellent virtual tour. So next on the program, we're going to look a little bit, turn towards the future, new capabilities and new technologies. First at the NHERI experimental facility at UC San Diego, and we will have two presentations by Professor Gilberto Mosqueda and Tara Hutchinson. So Gilberto, you may have technical difficulties from what I can see, or you are muted in case you don't know.
I'm sharing my screen.
Great.
So, sorry, just last minute I got a call from the doctor's office. But yeah, here we go. So can you see my screen now?
Yeah, yes, looks great.
Yeah, okay. All right. So I'm going to talk a little bit about hybrid simulation and echo activities at the site, and then Tara will follow up with some of the new equipment we're providing at the facility for easier access to testing. And so I want to start with, I assuming that many of you are familiar at least with what hybrid simulation is. And here at the facility, we have, having the largest shake table, we have, we could provide new opportunities for testing very large structural systems on the table. And this could even be further expanded later on, as we'll see with the new testbed facility we're providing in terms of substructuring different structures. But we can do different things. One of the advantages of hybrid testing is that you can take a very large structure, maybe even larger than what could typically be tested on the table, and you could test the key components. So for example, you could test, if you wanted to test like a tuned mass damper effect, upper stories of that are isolated in a building, you could test that part as shown on the figure on the left, and then model the other part numerically. And then in the figure on the right, you can see that we could test, for example, an entire building and then model the soil structure interaction effects in the computer as well. And vice versa, we could also test the soil structure interaction effects on the shake table using our soil boxes and model the structure numerically. So there's many different combinations of that we could do with hybrid simulation, and where we could test larger structures that can fit on the table, just test them, just combine them with the experimental and numerical modeling. So what we have at the facility, this is our current setup, and with the upgrade, we expect to have a very similar set of hardware. All this will be upgraded as part of the system, but we have the shake table and this controller, the MTS469D. We have an external Flexus controller to control external actuators if we want to have, for example, an actuated device within our structural system. And then we have high performance computers. We have 2 available. All these computers are connected within a ScramNet ring for fast real-time communication. Then we have 1 computer we've been able to run OpenSeas and OpenFresco in real time. The computer is not real time, but it's able to run fast enough for real time depending on the structural model. Another one running Simulink. And again, all these are connected together for hybrid, to enable hybrid testing, for real-time hybrid testing. One thing, because we are doing a shake table test and we're developing inertial forces, we usually have to do real-time hybrid testing for these applications. So the hardware and the speed of the hardware is critical for these tests. This is the same systems I just described and kind of listed out now. And what we have in terms of the ScramNet, the different control systems, and XPC, Simulink real-time programmable environment for user applications. And then we do have 1 actuator on site. We have additional actuators available in our additional campus laboratories that we could use as need be for the actuation system. And we have, depending on how you want to apply the system, we have for hard real-time applications, I mean, everything runs in strict real time. We can use, we can apply our numerical models in Simulink. And we could do this if the model is simple enough. We could program it all and run it in real time. If we want to have more advanced structural models, we could integrate OpenSeas into the system and take advantage of all the modeling capabilities within OpenSeas, including the highly advanced nonlinear models. The one limitation is we are limited to a special set of integration algorithms that are suited for hybrid simulation. Right? The other thing when we involve OpenSeas is that, at least how we run it in the past, we have not implemented in a real-time application. We've actually done it on a regular Windows computer and just run it, and to the point where we're running it fast enough to the point where you could keep up with the numerical simulation. But it's not hard real time, and we have safety mechanisms in place in case it doesn't achieve. For example, we don't return the command in sufficient time. We also have, we're very familiar with delay and error compensation methods that are critical to the implementation of real-time hybrid simulation. So what we have available in the lab is, for example, you just want to do a pure Simulink hard real-time application. We have Simulink models that provide the inputs and outputs to receive feedback from ScramNet. It could be from different data acquisition channels. It could be from the shake table itself. We could get that feedback, send it to the control system, to our programmable environment, and then send the feedback out, including commands for the shake table. We could send displacement or acceleration commands, but we found that displacement commands typically work better. Accelerations tend to be a little bit noisy for control of the shake table when generating these signals. In our more complex application, when we want to look at complex models using OpenSeas, we have, for example, this is kind of the layout of how the hardware will be and the communication, but we could have a very detailed model in OpenSeas, for example, and then that communicates through OpenFresco middleware to our XPC real-time system. And once you get to this XPC real-time system, from this point on, everything is running on real-time hardware. In XPC, we basically implement some type of predictive corrector to generate a smooth signal and transition from the OpenSeas model, which is not necessarily real-time, to the real-time environment. And we generate the commands to the shake table, which are then implemented onto the shake table. We get feedback, and all the red arrows are all the feedback coming back, which could be, for example, the base shear of the building that we need for the numerical model. Right. So basically, for this building model, we send a displacement for the command for the shake table, and all that comes down, moves the table, and then you measure back feedback, including, for example, base shear that would be a feedback to the hybrid simulation model. To demonstrate the capabilities, we did a couple of years ago conduct a commissioning test on LH Post. We did this only in the 1 degree of freedom configuration, but we implemented with a simple model. We did, well, we had a 1-story through a 5-story building model. On top of it, a tune mass damper. This is assuming all for a shear type building model. And so our experiment, in our numerical and experimental setup, we tried different approaches on how to implement the hardware. We tried the 2 different approaches, all full real time, and for a single degree of freedom system, and then for a 5-story model, we only implemented that in OpenSeas. Again, we could have done it in the hard real time environment, but that takes a significant more challenge for programming in something like Simulink. You have to program it all in the Simulink environment. We use a shake table in displacement control. We did initially try acceleration control, and that was too noisy. So we ended up going with displacement control. And that's kind of, in the literature, that's kind of what everybody seems to be doing in terms of control for shake table substructuring. We also tried 2 different integration algorithms that are available in OpenSeas, the alpha operator splitting and the explicit KR alpha method that was developed recently at Lehigh. And also we were able to accommodate the delay of the shake table, which was somewhere on the order of, I think, 20 milliseconds or so. We were able to accommodate that delay through an adaptive time delay compensation, in addition to a lot of the feed forward algorithms that are already implemented within the MTS control system, right? And so we did single and multiple degree of freedom systems. Our experimental setup was just the upper part, or essentially our tune mass damper on isolators. We wanted, because this is mainly a development project, we wanted something that could be nonlinear and have repeatable behavior. So we used the friction pendulum bearings on top of a rigid mass to represent that isolated mass on the system. Our system was rather light at 56 kips, and we had load cells here. For this level of loading, we could use load cells to measure the base shear of the structure that was a feedback for the numerical model. For larger structures, we would have to rely on measuring the force on the platen and then subtracting any friction and mass inertia forces. And we have done something like that before on shake table type substructuring. Yeah, but for this one, we had direct measurement of load cells that were located directly under the bearings. In terms of our experimental results, we were able to show that we can achieve real-time hybrid testing for the system. This is a comparison of the displacements and the measurement of the displacement at many points along the system, including the command and the measured. If we, while the displacement looks great, when we look at the overall plot, if you zoom in, you do see some differences. But the key when you want to look at it is the displacement target. This is in yellow, the displacement we wanted to achieve. What the controller is actually telling, after all the compensation, what the controller is actually telling the table to do, and what the table was actually doing in the measured. The orange and the purple are both measured signals in different tests. And you can see kind of the difference of how through this compensation method, we're kind of trying to get towards the right solution. But anyway, with all this, with the implementation of all these displacement compensation and all these different algorithms, control algorithms, we were able to get a sufficiently accurate response of the shake table to get reliable results from our hybrid test. A comparison of the real-time and the computational Simulink driver also showed that we got similar results when we repeated the test. Again, these were done on an isolated, the experimental part was a friction pendulum isolated device, and with very repeatable behavior. You could tell as we repeated the both tests, either in the pure real-time environment or in the measured whether OpenSeas or in Simulink real time. We got very similar results for both tests. This data has been published in Design Safe. The resulting algorithms, simulating models and all that is available on Design Safe as a published data model, and was actually used for the development of the hybrid simulation model in Design Safe. So you can look up the project, the data, and access to some of the simulating, some of the algorithms, for example, that were used in these simulations. Again, this is a view of the hybrid model. Lastly, I want to discuss some of the echo activities at the facility. You know, as the user to the facility, we offer partnerships with the different infrastructure we have available to enhance your echo activities at the facility. Our main goals of our echo program are to support the technology transfer to practitioners and future engineers. A lot of our past research projects, as we talked about yesterday, have led to the changes in code guidelines. And so, you know, we're happy to support that. You know, these very high level landmark tests usually lead to, could lead to significant changes in the design of structures. We want to innovate. We want to highlight our innovative research conducted at the facility, and you know, through websites and media and different relations, help you get that research out. We want to demonstrate the benefits of research to the public and critical decision makers. We have, through the partnership with our School of Engineering, the JACO School of Engineering Media Relations Groups, have reached out to local news and other audience. We want to broaden the participation of underrepresented groups in STEM, and we've done quite a number of outreach activities that I'll show one in a second. And want to develop undergraduate and graduate students through research training in the laboratory, and involving them in some of the largest earthquake engineering simulations research that is being conducted. And also provide a unique and simulating experience for undergraduates in high quality engineering research. This is just a quick video of one of our outreach activities in which we invited students from local schools. They all were able to build out of Connects different models on the shake table. And you notice that the decorated background is supposed to represent San Diego, the Coronado Bay Bridge. And the students have a blast doing these activities, and hopefully it encourages them to apply to or think about STEM in their careers. With that, just to conclude on this part, you know, we're very happy to support your activities, and especially the implementation of special initiatives like hybrid testing or echo activities at our facility. And we're happy to provide support in any way we can. And we look forward to even newer opportunities as we upgrade to the LH Post 6. With that, I'll turn it over to Tara, who's going to talk about our test bed structure.
Okay, thanks, Alberto. 1 second. Okay, are you able to see my screen in the presentation mode?
Yep.
Yes.
Okay, great, thanks. Well, thank you very much, Alberto, for the excellent presentation. We hoped that we could extend this discussion regarding new capabilities at the LH Post 6 NHERI facility by sharing with you a relatively new development of the operations group. That is something we hope will enrich the site's capacity to support community research in the coming years. Specifically, this involves the development, the deployment of a modular testbed building. Let me put this in pointer mode. Sorry about that. There we go. This work is supported through an NSF supplement to the Facilities Operation Award, and it's being undertaken by myself and colleagues Chris Pandarolides and Gilberto Mosqueda, as well as 2 doctoral students, each at the University of California, San Diego and the University of Utah. We're thankful as well for the support of several important industry sponsors, that is namely Corbrace, Durafuse, and SME Steel. They've been instrumental in supporting us with design ideas and, importantly, donating materials and manufactured components for this test building. So what is this modular testbed building about? Conceptually, it's intended to be a community available building for NHERI users at the Shake Table facility, so it's strategically designed to adapt to the table. Presently, we're in the design phase. We've procured nearly all of the materials. Importantly, it'll be the first structure to be tested on the newly upgraded LH Post 6. We have a short window of time to perform effectively a shakedown of the test structure and document its response characteristics for community users. The evolution of this effort really came through a number of NHERI workshops like this, folks discussing a variety of things they were interested in doing at the site, yet concerned about the ability to get those seismic demands into different components. We were fortunate to bring these issues to a number of manufacturers of conventional steel components, and they were forthright in their ability to come forward and help us with procuring these materials. So through close collaboration of yourself, future users, industry partners, and the work we've done with Utah here at UCSD, we've evolved into this reconfigurable and reusable modular testbed building. We're affectionately calling it the MTB squared. The idea is to really enable some low-cost testing of components and systems under simulated dynamic 3D loading. And you see some rendering here on the right of 3 different plausible configurations of the test building. So we're strategically designing this and going to be making available to the community all of the pieces and parts, let's say, to allow the user to move from left to right of this diagram here that you see of the longitudinal bay of the structure. In one configuration, you see a series of floor-to-floor buckling restrained braces. In a subsequent configuration, the structure is adaptable such that the lower floor of BRBs can be removed and a soft story mechanism emulated at that lower floor. Finally, in the last schematic on the right, you can see that all BRBs can be removed and instead, or rather engaged, shear fuses in the form of moment frame action at every level of the structure can be invoked. So that's the vision, really, to offer modularity in terms of its nonlinear behavior in 3 distinct characteristics along the longitudinal bay. Along the transverse bay, we've largely focused on offering the user a relatively stiff all BRB, let's say, structural fuse type configuration, though those BRBs can be replaced, and we've been discussing with core brace adaptability. That would be an opportunity for future users to investigate, varying strength and deformation capacity of BRB or other systems in a chevron or other brace configuration. So that's the idea conceptually. We selected early on in the process an archetype building, and we chose a 3-story structure just to allow sufficient elevation, but not impede upon the complications to support applications which would be multi-story, yet not so complex in terms of its erection. So you can see that the dimensional layout fits right, nests right within the floor plan of the shake tabletop platen at 32 feet by 20 feet in plan dimension. Story to story heights will be fixed. That's not an adaptable feature at 12 foot each. And all of the fabricated steel has already been procured for the dimensional layout you see here. The process we've undertaken for design is to take a look at selecting a high seismic zone and high risk category of downtown Los Angeles. We've utilized a family of recorded motions. Specifically, we obtained a motion suite that the upgrade team has been using in the process of the upgrade to address the fidelity of the new layout of LH Post. We've scaled those motions to within 90% of the MCE. And then I mentioned early on that there are 2 doctoral students working on some background analysis of this test structure. So we adopted 2 different finite element simulation platforms, OpenSeas and the more widely used design software of ETABS, to undertake a series of predictive analysis as we're moving through the detailing of this structure. What do we expect out of this structure? You can see some renderings of the ETAB isometric models in the special moment frame configuration on the left, the BRB1 configuration, all BRBs at all floors of the longitudinal bay, and the BRB2 configuration where the soft story mechanism is allowed to be invoked at the first floor. These models indicated a period range spanning from about 0.2 seconds for the BRB in the transverse direction to more than double that, 0.46 seconds for the special moment resisting frame or shear fuse type moment connection in the longitudinal bay. So you can see a wide range of anticipated dynamic performance that can be strategically adopted in the selection or utility of the modular testbed building. We've, of course, conducted using these models a series of nonlinear pushover analysis. You can see a family of curves here. The red curve being the most, let's say, ductile but softest system. That is the pushover of the structure in the moment frame direction. Limit states anticipated around 4% drift, though we don't anticipate taking that structure to that point. I'll show you the detailing for those connection level models in a moment. They're quite adaptable and intended to be strategically replaceable elements. Once you get into the BRB configuration, of course, the system is stiffer, and a uniform stiffness can be envisioned in both directions, is designed in both directions. And then it becomes the axial strain in the BRB that is the limit state, and you can see the range of attainment of those axial limit strains, and how they relate to the global roof drift targets. And so these are the types of performance curves that we hope to provide the users. The user, obviously, after the shakedown test next year of the real structure, we can improve upon these and offer some models for future users to adapt and attach elements to the system. How did we undertake this exercise? Well, we went through a series of connection level models. This is some work by Junwei Liu using the OpenSeas tool to validate a series of tests conducted by Paul Richards in the development of the Durafuse. This is the exact Durafuse connection that's going to be used. You can see a little bit more detail about the simplified shear plate and how that's intended to be the yielding mechanism. It should be easily replaceable. That's the intent. And Durafuse will be providing us those during the shakedown procedure so that they can be replaced after they're demonstrated to yield in the system configuration. So the model does a very reasonable job. The phenomenological model does a very reasonable job, and that was placed into a system level model. And one interesting thing we think about this opportunity to utilize this modular testbed building, and now in all of the hard work that's gone into the newly configured LH Post 6, is the opportunity to investigate the effect of multi-directional input excitation into lateral force resisting systems. And you can see a series of analyses here performed by Michael Morano, another the second PhD student working with us, where he's taking a look at sequentially input excitation in one direction, then the alternative direction, and coupling the input motion scaling those motions and at a first cut, looking at the peak base shear. And, you know, the enhancement in terms of demands when bidirectional motions are imposed upon a building is apparent and known, yet, you know, not considered, let's say, per se in design. And so, you know, obtaining real physical data like this and looking at how this is going to affect the elements that attach to a building is going to be an important contribution, we think, with the availability of this modular testbed building. In like fashion, in terms of the analysis, what we've been doing is sequentially taking a look at the behavior, the expected behavior of the frame during a loading sequence. And so you can see here clearly, one can envision a series of limit states being obtained in each of the bracing elements. Where and when those occur is something that designers, you know, are interested in. The lowermost would be expected. You can see the trace and the behavior as it's tracked during the loading sequence, during the sequential imposition of lateral top drift. This is just under a pushover analysis, and you can see these bubbles emerging in his analysis to identify at what global drift these are occurring and when they are occurring. So this is the type of pre-test simulations that we're performing in an effort to track the performance of the building and offer our best assessment of the performance and in the design phase. An interesting feature of this structure, and we've wrestled a little bit with this, to be honest, is how to detail the floor diaphragm. I should be sincere in the sense that when we went down this road, actually, we ourselves as investigators were interested in looking at the performance of vertically distributed non-structural systems in the building. And so we were able to take a first step and get some support through this supplement to design and construct and shake down this test building. And take a look at its capabilities across the board of applications of interest. But in all sincerity, we initially envisioned a fairly perforated diaphragm. You can see these blue or these cyan regions. We imagined that these would be open, and we offered them as sort of an egress study space, specifically thinking about stairs that could be spanning from floor to floor. So to compensate for the needed mass, thinking first just about the mass, we searched around our facility to see what masses were available, and we plopped in some lumped masses at every floor. That's an economical strategy to adopt here. However, the reality is that the diaphragm still isn't stiff enough, even with a series of core interior framing, and it became fairly cumbersome. So we've been fortunate to work with University of Massachusetts Amherst and some industry sponsors. A shout out to those colleagues at Verco, AISC, and the Steel Decking Institute for coming forward and helping us come in and define some modular floor deck solutions. And so a relatively new feature we've augmented to this building just within the last weeks or so is this idea that the user of the testbed building will also have at their utility some modular floor decks to drop in at every floor. We're going to be constructing on site and as well testing 6 lightweight modular floor decks and 6 heavyweight modular floor decks. The lightweight solution is something you might more typically see in a warehouse building or in maybe the roof of a building. It's simply sheathing over steel decking. A heavyweight solution might be more of a typical live load type of application of an occupied building. We might have a composite decking over a poured in place concrete. So about twice the floor to floor weight. In totality, just out of interest, the structure is going to weigh on the order of just under 150 kips when all lightweight floors, let's say, are in place, and approaching 170 kips when all heavyweight floors are in place. So that's where we are with that structure. Just a few concluding remarks. This MTB squared, is intended to be a community available, let's say, vehicle for delivering a wide range of seismic demands to attached elements. We envision, it's supporting the study of various seismic protective systems, lateral resisting systems, contents seems to be a natural opportunity, particularly with the floor space, and a wide variety of non-structural systems. We started this journey thinking about stairs and egress within that drop-in central floor region. That's still a plausible opportunity for the community. Facades, perimeter enclosures. There's a very easy attachment to the perimeter of this structure. Floor mounted or hung mounted mechanical, electrical, plumbing systems are a known issue in terms of their understanding their seismic response. Floor to floor interior wall assemblies, and we hope the community will think of others, of course. As this structure will be the first tested upon the opening of the upgrade of LH Post 6, my last remark here is that researchers may prepare proposals to utilize the MTB squared in their work in the coming years, and we're available to answer any questions you have about the structure, its design. The intent is, after the shakedown experiments next year, upon the opening of LH Post 6, to prepare a detailed report, make that available in the community repository. So with that, I'll conclude, Karosh.
Thank you very much, Gilberto and Tara, for your excellent presentations. And so if you have questions, please write them down. Keep them for the question and answer session that will come up soon. But now, let me see how we're doing with time. I think we are doing very good with time. So the next presentation will be given by Professor Jeffrey Berman from the University of Washington on rapid equipment and examples of large-scale experiments. Jeff?
Yeah, thanks, Joel.
It's yours.
Thank you. Can you hear me okay and see my screen?
Yep.
See the PowerPoint? Great. Okay, yeah, so I'm going to, I guess the objectives of this presentation, we'll start there. I like this photo because it's three people thinking about this upside down building, and that's really what I want to do in this presentation, is to get people thinking about how rapid tools can help you learn more about your experiments. We want to generate interest in using the rapid tools to support data collection, both in the laboratory and in field experiments. And of course, in this joint workshop, focusing specifically on applications that might be interesting for the UCSD shake table for LH Post 6 in its new configuration. We want to spur ideas also for innovative measurement and processing methods. I think that's something that's really important to us at the Rapid facility. We don't want people to just be collecting data with our equipment, but thinking about new ways to interpret that data, new methods to process that data, all of those things. I think there's lots of opportunities to do that in controlled laboratory environments. And then we want to consider unconventional uses of the Rapid equipment. I'll show one kind of towards the end that I think is really neat, and hopefully to get get you thinking about how you might use our equipment in really unconventional ways. So rapid deployments to experiments. I thought I'd just take you through 4 of these. I'm not going to talk about all 4 of these. A couple of these are going to be talked about later on in the workshop. But I will talk about 2 of them, not in great detail, but a little bit. So the 2 I'll talk about are right at the top. The capturing wave evolution with LiDAR. That was a project that was conducted for Adam Young at Scripps and UCSD, and this was done at Kelly Slater's Surf Ranch in California. And Joe yesterday showed I think one slide with a photo of this, and so we'll look at it, what they did in a little bit more detail. And then we have, and then I'll talk about just relatively briefly a deployment that we did to the eDefense Shake Table facility in 2018 to support a team led by Maria Kolu at Texas A&M University. And that was to monitor progressive damage, development of damage to structural and non-structural elements in light frame timber buildings. And then later today, Paulo Calvi is going to talk about a more recent deployment to the E-Defense Shake Table facility to investigate damage to a reinforced concrete moment frame that was being tested. And I will leave him to talk about all the great things that are going on with that project. And then in our panel discussion towards the end, Paulo will be joined by Jonathan Hubler of Villanova, who deployed rapid equipment to monitor blast-induced liquefaction in a field experiment in New Zealand. And so he'll share a few slides on that at the beginning of the panel discussion. So I wanted to highlight quickly what I feel like are probably the most obvious pieces of equipment that can be used in conjunction with large-scale tests, but I don't want to close the creativity off in just these pieces. I think we also have other pieces in our portfolio that could be really interesting. But certainly, as we'll see, there's lots of opportunities to use LiDAR in experiments. Paula's going to talk about some dynamic measurements that we've done with LiDAR. I'll show later the dynamic measurements that were done with the waves at the surf ranch. And so there's both dynamic and then also a lot of work that can be done on kind of post-test investigation using LiDAR and post-test damage documentation using LiDAR. And there's and again, Paulo will dive maybe even deeper into that than I will. I think there's opportunities to use UAS systems. The facility at San Diego actually has experience using UAS systems and video in conjunction with high-resolution GPS equipment to actually track dynamic displacements of structures on the shake table. And so I think there's lots of room to continue developing those methods. We also have an accelerometer package. There are nanometric Titan accelerometers, and so those are they are complete what we call building systems, and we have 3 of them. Each building system contains a set of 3 triaxial accelerometers, a GPS antenna, cabling, and a data logger. And so I think deploying those in field experiments or to laboratory experiments to supplement existing instrumentation is also possible. We have the MASW system that's been used in some large field experiments. Like I said, we have these seismometers that have been used in field experiments. These last two, the MASW and the seismometers, I think complement the available instrumentation that are available with the trucks at the UT Austin NHERI facility, the geotechnical shaker trucks. And there's some real possible crossover for field experiments there. And then, of course, I'm asking you what else might be out there for applications. I wanted to just highlight the Leica P50, which is our highest accuracy and precision laser scanner, and is currently really the best available on the market. And it's the one we're recommending right now for use for damage detection in large-scale structural experiments, such as crack detection and quantification. Okay, so the first project that I'm going to highlight in detail that uses some of this equipment is actually not an experiment, but I think a lot of the takeaways can be, there's many takeaways for thinking about applying our instrumentation to large-scale experiments. And so it's actually a reconnaissance. It's not a shake table test or a laboratory test, but it's data gathering on large scale structures. And so I think the lessons are really directly applicable. It's a project I was involved in. It's reconnaissance of large volume low-rise building collapses and partial collapses in Hurricane Michael. It was collaboration with David Roche and Justin Marshall at Auburn University. And you can see the NSF awards, and all of the data that I will show is all archived at this link on DesignSafe and publicly available, including the complete LiDAR point clouds, LiDAR-derived point clouds, processed and unprocessed. Just real quick background on Hurricane Michael. It was a Category 5 hurricane, made landfall in October 2018. Just for reference, we had opened the doors of the facility to users on September 1st, 2018. So this major event was really one of our first opportunities to get out and use our equipment and do really large scale reconnaissance effort. Recent wind 150 miles an hour, over 7 feet of storm surge in some areas, heavy rains, impacted Panama City to Port St. Joe in the Florida Panhandle. Very devastating event. So there was a flurry of reconnaissance activities that happened for Hurricane Michael. There were several steer teams that were assembled. There was a virtual assessment team, a field assessment team. Both those teams produced reports very quickly. They are what STEER calls the early action reconnaissance reports and the preliminary virtual assessment team reports. They were both produced within about a week and a half of the event of the hurricane making landfall. And the STEER teams themselves, the field team was in the field really about 5 days after landfall and spent about a week in the field. The observations from those teams made it clear that there was an extensive damage to rise, large volume buildings. These are warehouse type buildings. The failure rate seemed to be much higher than expected. And there was the potential, when you looked at some of these, there seemed like there was a potential for very similar failure modes between many of the buildings. So based on those reports and that preliminary assessment, a team developed a rapid proposal and submitted it to NSF. That was David Roche, Justin Marshall, and myself. And we deployed along with Rapid staff. At that time, our site manager was Jake Daphne, who is now returned to practice in geotechnical engineering, and Sean Young, who you saw in the video as well. And so we all deployed. We took UAS equipment, a DJI Matrice, UAS with camera and a Phantom. We also took the Leica that was BL360 and the Tech EyeSight XR3. The XR3 is a long-range laser scanner. The BLK360 is a short-range laser scanner. And we actually were successful in combining those point clouds. We took GNS receivers for ground control. We took the robotic total station, cameras, iPads, and rat packs as well. And you can see us kind of assessing one of the large volume buildings. This is a damaged building near collapse on Tyndall Air Force Base. You see our whole setup, the GPS systems, we're getting the long range scanner set up, we're flying a drone, kind of all happening all at the same time for one of these buildings. Just to give you an idea of life in the field, and I say this because I've also been to eDefense twice now for deployments to the Shake Table facility there, and the schedule was amazingly similar for whether you're doing field reconnaissance or whether you're kind of deploying our systems at a Shake Table. It's, pre 7 a.m. You're out the door with the equipment ready to go. Long days at the site, taking all of our measurements. So we would set up the GNS space stations, we'd fly the UAVs, We'd scan as much of the building as possible with both short and long range scanners. We'd mark ground control with a rover GNSS, survey control points with the total station, make any conventional kind of hand measurements of structural elements we felt was necessary. We generally sent Justin Marshall out to scout the next building for the next day, and then ended field work shortly after dark, and then eat some dinner somewhere that might have been open, and back up data and charge batteries until well after midnight, and break for the next day. So that's life in the field, and like I said, that's a very similar experience to I think what Paulo will tell you about what we were doing at the eDefense Shake Table for experimental deployments. So I'll go, I'm not going to spend really any time on this. We have a lot of specifications on our equipment on our website. So you can look at the individual specifications of the LiDAR systems, but this was the BLK 360 that was used extensively in this project. I think the most important thing is the 4 meter accuracy at 10 meters, 4 millimeter accuracy at 10 meters and 7 millimeter accuracy at 20 meters, to give you an idea of kind of the accuracy of a single point collected. And this is a really fast scanner. It does a full 360 degrees horizontal, 300 degrees vertical, and takes about 3 minutes to do that scan, maybe a little bit longer. Then we also had the XR3 in the field. The XR3's accuracy at distance is really, really good. So 5 meters or 5 millimeters is at quite a distance. Its repeatability of plus or minus 4 millimeters. So that's the kind of the placement of a single point, plus or minus 4 millimeters. And acquisition rate, very quick acquisition rate for the number of points it's producing. And so to give you an idea of the buildings that we surveyed, so we did about 5 or 6 buildings on Tyndall Air Force Base. And then we also did these other buildings kind of spread around Panama City. And you can see those there. So this was what a typical collapsed large volume building looked like. One of the just to point out kind of the interesting features. So this is the West Rock East Terminal building. We noticed collapse of the wall that was parallel to the long span girders. And this was very consistent really in all of the buildings that we surveyed. And as I'll show later, it turns out that the buckling of the purlins that was used to transfer the wind load from this face through the roof, perpendicular to the long span girders, and then over to the walls of the building where you would see cross bracing. It was the buckling of those purlins that was the cause of collapse in the vast majority of the buildings that we surveyed. Similar, here's a marine storage building. This is the Watson's Landing Marina. Again, collapse of the face of the building that runs parallel to the long span girders within the building, and buckling of the roof purlins. And again, we'll show those over and over again. This is a slightly different building. It's it's called the Intermodal Distribution Center. A lot of FedEx stuff came out of here, and kind of a transfer hub for a lot of different equipment. This was actually a tilt-up building with tilt-up walls. But again, the collapse is again parallel to the long span. In this case, they're not girders, they're trusses in the long span direction. And this collapse was perpendicular, was again collapse to that parallel wall. And we think even though it's a tilt-up building, there was maybe some failure of the tilt-up connections, but eventually the buckling of the purlins, trying to transfer that wind load back into the lateral force resisting system in the long direction of the building was problematic. And again, one last example of an aerial shot from our UAV. This is a distributor, a distributing warehouse for Miller. So there's actually a bunch of kegs of beer in here that you can see, which is a real shame. And again, the collapse was the wall parallel to the long span truss framing. So we went through and we did lots of data collection. You saw us in the field there collecting both LiDAR and SFM images. The way we processed this was we registered the LiDAR scans first without the survey control. Then we processed the UAS images to produce SFM models of the exterior. And this was done again without survey control. It was just taking us a while to do the control point processing using the GNSS and the total station data. But once we did calculate those, we incorporated those control points into the LiDAR registrations. And we still have work to do on this in combining the control points into the SFM models and actually combining the SFM models with the LiDAR of the interior and some of the damaged areas. So the idea is that we'd have the SFM derived point clouds of the exteriors from the UAV flights and the interiors of the building done with LiDAR, and we put those two things together. And so that last step still is not done because the processing really does take quite a long time. And the student that I had on this project is gone at this point. But here's some of the point clouds. So this gives you an idea of the type of data that could be collected, whether in a shake table test or a field deployment of a structure. So here's the point cloud produced for the Miller Distributing Building, the West Rock building that I showed, and the Panama Distribution or the Intermodal Distribution Center. And you can see those. So I want to take you through a couple cool videos that we put together. These are fly-throughs of the point clouds. I think they do a nice job of illustrating the value of LiDAR. So you'll see flash in and out the cleaned point cloud versus the kind of raw point cloud, where we're removing things that aren't necessary for evaluating the structural system. So there's all the kind of background removed, all the shrubs and stuff, and now we're isolating the structural system. You can see the collapsed tilt-up walls. You can see the trusses spanning the bays. You can see we kind of get right into the interior of the building. We can bring back the unclean point cloud, and actually now we'll see removal of a lot of the debris that was there in the area. So we can take all the measurements that we would need to assess this structural system. This is one that we were not able to get drawings for. So being able to assess everything about this system from the LiDAR process LiDAR cloud is really necessary in order to develop the structural models that Justin and David are doing with their students at Auburn to assess why these buildings failed in the way that they did and make ultimately some building code modification recommendations. So one more fly through because they're too cool not to show you. So here's a fly through of the Watson's Landing Marina. Again, you see the clean and unclean point clouds kind of alternating back and forth. So we're going to go in the undamaged bay. And these renderings you just do in the software. This was not a flight direction or anything like that. These are all from terrestrial LiDAR scanners. Actually, you can see some of our scan positions pop up. Those are the circles. And one of them, you can even see one of the scanners set up. So you can see this is great detail from this building. We were actually able to make really good measurements of the structural elements in this case. For this building, we were able to obtain structural drawings, and so we were able to contrast our approximation of structural element sizes from the point cloud to to the drawings, and we're doing a really good job of approximating the structural systems from there. Using all of these models, we've established what we think is the kind of key common failure mode between these buildings. And like I said, we did a dozen buildings. I've only showed a couple of them here. When we have the windward wall as the short direction of the building, we're asking that that load to transfer up into the diaphragm. And the first location of cross bracing in this building is actually one bay back. So that wind load has to go up into the roof diaphragm, transfer as compression in the purlins, and then again, back through the wind diaphragm, or back through the roof diaphragm into the cross bracing that's one bay back. So we're asking these purlins to be under really large compression to transfer that wind load back. At the same time, you have suction on the roof because the wind speed is really high. You're pulling up on those purlins, so they're under combined bending and compression. And we were able to identify that failure mode. And really the point clouds have been very helpful in doing that. This is a disastrous collapse of this beer distributing warehouse. But again, we're able to extract the key structural features. So the long span girders and the purlins themselves that are all crumpled and buckled. Again, this is the short span, the short direction of the building where the long span girders are, and the buckled purlins. And so evidence of a very similar failure mode for this building. And then just showing kind of clean and uncleaned point clouds and the types of measurements that you can do with LiDAR that you can't do by hand because there's all this stuff in the way. And with LiDAR, we're able to extract only the salient features that we're interested in. Okay, and so we are hopefully informing models, performing and performance assessment. So like I said, Justin and David have computational models of these buildings that the LiDAR are informing, the LiDAR data is informing. There's potential impact on design codes, and we're inspiring research. So that's one application of LiDAR in these buildings. And these other example projects I'll go more quickly through. So I'll show you a little bit of the data that was collected, again, using our LiDAR systems for a deployment to the E-Defense facility for tests on light frame timber buildings. That was through a rapid grant that was to Maria Kolu at Texas A&M University, along with Kerry Ryan and Shade Dashti. We deployed, this was an interesting deployment in that everything happened kind of very quickly. We had great interactions with the PI team. They sent students and a couple of the folks who were going to help deploy their equipment to train on the equipment at UW. And then we also deployed a couple rapid staff to do some field training with them for about 2 days, and then they came back. Then the staff came back, and the researchers conducted the rest of the data collection themselves at the E-Defense facility. You can see Maria and Kerry doing a scan of an exterior of the building with one of our that's one of our map tech systems. So again, the BLK 360 and the map tech system were deployed for this experiment, along with the robotic total station to make some point measurements and do some control. The map tech system is no longer what we're going to recommend for this type of work. Unfortunately, at the time of this deployment, we didn't have the Leica P50 system. If we could do this project again, we'd have sent the P50 system and gotten even higher resolution imagery, point clouds, and maybe been able to map out cracking a little bit better than we were able to do with the BLK 360 and map tech. This is a constantly evolving field. The LiDAR equipment is always getting better, and the Leica P50 is like I said before, our choice now for doing this type of this type of work. However, we were able to obtain sub-centimeter level accuracy point clouds on these two buildings before and after testing through 6 ground motions. And just to give you an idea of the damage on these buildings were not as extensive as we expected it to be. Pulling out damage when it's not that extensive is even harder, but there was a fair amount of non-structural damage that was captured in 3 dimensions at that high accuracy with these scanners, and you can see some of the non-structural component damage. Here, we also discovered residual building torsion that was unknown to the Japanese researchers and to the conventional instrumentation that was used in the experiment. And so I think that was of great value to the research team overall, not just the US researchers, but the Japanese research team as well. One final walkthrough of an example project is characterization of these waves with LiDAR. This was done by Falk Feddersen and done for Falk Feddersen and Adam Young, who are UCSD and Scripps Institution of Oceanography researchers. The funding, this was not an NSF project. The funding was provided by the Mark Wolfinger Surf Zone Process Research Fund, and also the campaign for UC San Diego and Scripps itself. And so here for this work, we sent our Mini Ranger, which is our LiDAR equipped UAS system. And so here's the surf ranch. And so, usually what's done here is actual surfing, but they're also using it to study waves, which I think is a really awesome application of the surf ranch. They had some LiDAR mounted on a rig that they were using themselves, and they were able to do line scans. So Paulo will talk a little bit more later about line scan LiDAR data. So you're essentially taking super fast points, but you're taking them on a single line. And then our LiDAR on our drone is actually a mobile LiDAR unit. So it is actually capable of taking dynamic LiDAR measurements. And so they were interested to kind of use both of these to quantify wave break and quantify kind of, they're looking at wave dynamics. So just looking at the data from the UAV itself, they were able to really capture the dynamic wave break. So we have time on kind of the z-axis coming towards us. So this is a dynamic measurement of the wave break and the progress of the wave break in space. So really, really cool measurements to be done here. And you see there's noise in these point clouds. We're getting, little bits of water reflecting back. We're getting spray, things like that. But this is a really amazing measurement that could not be done without this type of equipment. And so I think the possibility for using perhaps our LiDAR UAV in dynamic frames, our LiDAR mounted LiDAR equipped UAV in dynamic frames. I think there's a lot of potential here to develop this work. This is certainly developmental. There's research to be done on interpreting the data. This isn't going to be an off the shelf, you set it up and you get the exact measurements that you want. We're going to have to work together to figure out how to make the measurements. But I think there's a lot of potential for doing this in the future. And then finally, a slight bit over time, but I know that actually we don't have our next speaker, so I'll maybe take 2 more minutes to go a little further.
Yeah, no problem, Jeffrey. We have extra time.
Yeah. So I just want to go back to what I talked about yesterday in how I think we can combine all of these tools that we have, field observations, laboratory experiments, simulation tools, and computational resources to really solve grand challenges in natural hazards engineering. And I'm just going to show one really quick example of something that we're doing really recently. This is actually, we did a deployment in COVID times out to collect data for a COPE project, which is Coastlines and People program at NSF. And this was to support an eager titled Coastal Hazard Planning in Time for Dan Abramson, who is in urban planning here at UW, and Bo Zhao, who is a geographer. And then also it incorporated Harold Tobin, who's a seismologist, Ann Bostrom, who's a social scientist, and myself just kind of leading the data collection efforts. And so what we did for this project is we deployed a whole bunch of equipment. There's a big list of the equipment that was out there, and you can tell it's COVID times because Joe and Andrew are out there wearing their masks. And you know, just to give you an idea, this is how full you know, the car was with all of our equipment when we went out to this town. But the objective of this project is to produce planning products, is to produce geospatial products that can be used in planning efforts for a coastal community in Washington State that has great tsunami risk. Okay, so here's the town. It's called Westport, and this is the Pacific Ocean over here. This is Gray's Harbor on the right-hand side. And so Westport is out on a peninsula on the Pacific coast. It has extraordinary tsunami hazard. There's kind of 2 roads in and out of Westport. It all is pretty flat, low-lying. I think the highest elevation above sea level is something around 10 meters. So very low-lying area. There's not a lot not a lot of high places to go. This is the site of the first tsunami vertical evacuation facility in Washington State. It's at a school that's on about the southern edge of the town. It's about down here if you can see my cursor. And so we have developed or are in the process really of developing a digital twin of this coastal town that then can be used for planning purposes. And so we're going to, our planning colleagues are going to develop new sites for vertical evacuation facilities. They're going to reimagine how some of the shared space, some of the parks that are around, this is actually a big state park here, can be repurposed to help the community be more resilient in the face of a pretty epic tsunami threat. So we went down, we deployed LiDAR and UAVs to map out at centimeter resolution the entire peninsula. And then we can take that information, we can use it for planning purposes, and also potentially use it for future research where perhaps we're developing a model of Westport in the Oregon State wave flume. You know, there's all kinds of very interesting things we can do. We did very detailed workups of some of the critical facilities. These are buildings around a wastewater treatment plant where we flew at lower elevation to be able to develop some higher resolution models of those facilities. And then we drove street view on every single street in the town, and we're working to combine to generate structure for motion models from those street view runs and combine them with the aerial flights. So we'll have really good kind of 3D model really of this entire community. So I want, just to spur people to be thinking kind of large scale. What can we be doing to combine field observations, take this information, move it to the laboratory, do a nice set of experiments that potentially help improve the resiliency of communities like this, generate computational models, and deploy design safe's computational resources to get these things done. So I think there's just so many opportunities for us to be thinking at these really large scales to help improve community resilience. And sorry, I went a little over. I took some of Joy's time, as I know she's not going to be here. But thanks, and again, you can follow us on Twitter and visit our website. And thanks again for coming to the workshop.
Thank you very much, Jeff, for your enlightening presentations.
Thank you. We have one question in the Q&A that I'll read out right now, so we can answer that. The question is, any idea about the wind directions for the damaged large volume low-rise buildings?
Yeah. So we're combining this. So, I mean, it's complicated, right? It's a hurricane. So the wind actually on these low-rise buildings, it rotates, right? As the hurricane moves past, the wind direction rotates. We're fairly confident that collapse of these buildings occurred when the wind direction was close to perpendicular to the short walls. So perpendicular to the long span framing, the long span girders. Usually the long direction of these buildings is actually perpendicular to the long spans. They'll pile up several of these long span girders to go back and make the building really, really long. And so when the wind was perpendicular to that, it is typically when collapse occurred. That's pretty clear from the damage that we observed and the modeling work that I didn't really show that David and Justin are developing. Thank you for that question.
Jeff, I have a question for you. What additional equipment would you need at the Rapid, or maybe you already have it, to perform digital image correlation in a dynamically, and first maybe in the lab and small scale, then larger scale in the lab, and then maybe in the field?
Yeah. So I think Joe talked about this a little bit yesterday. So we have a project that wants to be exploring capturing the dynamic propagation of rockfall. And for that project, we're looking at a couple high-speed cameras. And those high-speed cameras, that we don't have the high-speed cameras that would be necessary to do dynamic DIC at this point. But we are looking at them for that project. And as you know, all the sites are going through a renewal process for their next 5 years of operation at this time. And we have a list of new equipment that we would like to obtain in that renewal. And high-speed cameras are high on that list. And so we hope to have those capabilities moving forward here. In the tests that Paulo Calvi is going to talk about after the break, we partnered with Muhammad Mustafa at the University of Nevada, Reno, who has been developing a dynamic DIC system. And he deployed his system to the eDefense shake table to do dynamic measurements of key points on this 3-story reinforced concrete moment frame that Paulo will talk about. So we have partners. I know you have some partners as well, Joel, that work in this area and can help us develop the tools. But right now we are missing as a facility resource the high-speed cameras necessary to do that.
Thank you very much.
Mm-hmm.
Are there any other questions from from the panelists or the attendees?
Not at this time.
There is none at this time. So maybe now, Kurosh, we would like to take the poll again for those of you who were not here early this morning. Dr. Joy Poshki was supposed to talk now, make a presentation about funding opportunities at NSF, and she cannot. But she's open to make her presentation this afternoon at 1:30 during office hours. So we would like to take a poll of who would be interested to listen to her presentation so that we can send these results to her. If there are not sufficient attendees, then she recommends that those who are interested would contact her directly. So if you could please take a poll, maybe Kurosh, you want to add something?
Yeah, I just launched the poll. You should see it on your Zoom screen. The answers you provide are anonymous, so don't worry about privacy. And as Professor Conte just mentioned, if there's not enough people that are planning on attending, then Dr. Poshki has said that they can contact her directly. So we'll take a few minutes and allow you all to just answer this poll question so we can gauge the interest.
And if there are no more questions, unless you propose something else, Kurosh, maybe we should have the coffee break until 10:30.
Yes, if there's no other questions, we will do that. We will go on the break until 10:30, and I'll leave this poll open if people would like to respond. If you need to take some more time, it's not a problem.
Yeah. So I'm assuming that Dr. Poshki's presentation would be 15 minutes too. I mean, that might be good information for the.
Yeah, it would. It was
15 minutes would be the same.
Yeah, 15-minute presentation with 10 minutes for question and answers. That's what we had planned in the program.
Mm-hmm.
Maybe while we're thinking about that, one thing that came to mind, Jeff, I really enjoyed your presentation, by the way. You spurred me to think about one challenge we have when we get into taller structures that are on the outdoor shake table. We're always wondering where to, how to go about documenting the location of sensors on that structure. We out there with tape measures, et cetera, and we've used LiDAR scanners in the past, but if you now have a LiDAR mounted on a UAV, it could be actually, from the experimentalist point of view, advantageous to fly around and capture the exact position of those sensors. That could be really useful, actually, practical thing to do.
Absolutely. I think, one of the biggest challenges in these really big tests is understanding and remembering and properly recording the precise.
Yeah. You remind me of something we do in the Powell lab. Sometimes when we have buried sensors in saturated soil conditions, we need to protect them, and so we drop them into this gluey, substance that you put on the handle of tools. What is it called? Tool grip or whatever.
Yeah.
And maybe we need to get a color-coded one so that on the LiDAR, or on the images captured through the LiDAR, you immediately can see these sensors. They pop out at you.
Absolutely.
Some practical things like that in conjunction with your tools would be kind of fun.
Yeah. No, I think there's a lot of value in having having a 3D interrogatable model of your undeformed structure.
Yeah.
And all was there.
and actually after as well, because sometimes we expect, as you know, right? I mean, we have a joint or a connection, and we may be concerned under the high level of nonlinearity that a sensor moved. I mean, unfortunately, we may have hopefully we had a redundant sensor, but if we need to know if a sensor moved. And so even that before and after flight with the LiDAR mounted on the UAV could be really useful for a researcher.
Mm-hmm. Absolutely. Absolutely.
I have my next supplement to request with you, Jeff.
I think we've the tall mass timber
yeah,
coming up, and
yeah, there you go. Yeah,
a whole lot of opportunities here.
Yeah.
Any other question, maybe? New questions?
I don't see any other questions right now. Everyone has the option to unmute themselves at this point if you feel more comfortable asking your question instead of writing it down.
So then I propose maybe we take the break. So we will reconvene at 10:30.
That sounds great.
okay, thank you, Joel.
Okay, it is now 10:30, and I think it's time to get back. Hope everyone enjoyed a short little break that we had.
All right. So we are going to continue through the program now. And the next presentation will be by Dr. Kurosh Lotfizadeh. He's the site operation manager for NHERI at UC San Diego. And he will talk about example uses of RAPID-like tools in large-scale experimental programs.
Yes, thank you. Can everyone see my screen?
Yes, we can.
Okay, perfect. So today I'm going to discuss some example projects or uses of RAPID-like tools in experimental work. I'm going to briefly go over some of the recent experiments that I've done in the past, not on dynamic tests, on static type tests, not performed at the shake table inside a laboratory environment instead. I'm going to briefly discuss some of the tools that I use that were similar to what's available from Rapid, go over a few of these tests, and next I'll discuss some of the technologies that could be incorporated that are available that would be really nice if incorporated in large scale testing, especially in the shake table environment. And I'll go over the equipment and instrumentation that we have available at the LH Post 6. So first up, during my PhD studies, I performed a series of tests. The first was bar development and bond slip type tests. And what we were trying to do was to see if the AASHTO LRFD specifications for tensile development length equations were suitable for high strength reinforcement in reinforced concrete structures. What I did was I built 4 test specimens using number 18 and number 14 size bars, really large diameter reinforcing steel. And we did 5 KSI and 8 KSI concrete to see the concrete strength differences, as well as the bar size. We wanted to determine the equivalent strain penetration using grade 80 steel and provide a recommendation for the equivalent strain penetration term in the design codes. So each specimen was designed as a column with a foundation. They were well reinforced, well confined columns, and we had the sample bar that we were trying to investigate embedded in the middle, sticking out of the top of the column. And we had friction welded headers specifically designed for these high strength steel bars. And we had them friction welded onto the top of the bars. This is the number 18 bar and then the number 14 bar. And we had this this test frame with a vertical actuator, with an actuator mounted to the frame, where it would hook up to the threaded end of these headers, and we can use this actuator to push and pull this bar inside that concrete column to see the bond and determine the strain penetration. Now, this guiding frame worked really well in tension. As you can imagine, when you're pulling, there's no problems, but when you're pushing it downward, you have some issues with the compressive forces and potential buckling that would occur. So to mitigate the buckling and any unwanted rotations, we had to develop this guiding system where it would force the actuator to move only in one direction without having any rotations or out of plane movement. Just to show you a brief little video, I tried to speed these up and not bore and take too much time, but you can clearly see as you're pushing and pulling this bar, the concrete around the surface here starts to crack and fail and creates a kind of a cone failure, a fracture surface at the top of these columns where the bar is slipping inside the concrete as you're doing larger and larger load amplitude cycles. So one of the things you'd want to see is this cone penetration here, this fracture surface. Now, using some tools, at the time I didn't have access to LiDAR scanners or any of that nice equipment. So I was limited to using DSLR cameras and using open source software for SFM, I was able to get 3D point cloud models of the fracture surface of all 4 of these test specimens. So here are short little clips showing these 3D point clouds of the fracture surfaces, and using this type of technology, I was able to eliminate all the unwanted information and look directly at each type of fracture surface. And we can get very good information from these point cloud models that you otherwise wouldn't be able to get. Now, in this one case in particular, in specimen number 3, was interesting because the fracture surface was just massive and a whole bunch of the concrete had broken off, and it was really difficult to determine the exact cone, separate that from the other damage that had occurred at the top of the column. But again, using these point clouds, you're able to map exactly the cone of interest and get the information that I was looking for. So that was one of the uses that I did. Next, I had another experiment where it was a large full-scale column extending into a type 2 shaft. This column was 17 feet tall. It was a 4-foot diameter column, and it was embedded into an 8-foot tall, 6-foot diameter shaft. Again, entirely reinforced with grade 80 steel. And what we wanted to do was observe the behavior of high strength reinforcement in the plastic hinge region and in the non-contact splice region that goes embedded inside this shaft. We wanted to validate the replacement of grade 60, which is commonly used today in these types of columns with grade 80 reinforcement or even higher. But my main focus was grade 80. So just again, another brief video showing we had the loading direction in the north and south directions, and you can see the plastic hinge developing in the column. This video down here is the southern face, and the video up here is the northern face, and you can clearly see the extent of the damage as our loading cycles progress. Many of the bars fractured, and you can see these fractures. And as Professor Conte mentioned yesterday in a presentation, it sounds like a shotgun blast when these bars explode. And these being high strength, large diameter bars, it was very, very loud. Pretty soon you're going to see some bars fracturing here. And you can see the cover concrete has spalled. You're going to start seeing some buckling in the bars, and you'll see some fractures occur of the bars. And after that, you get the cone failure. Up on this top one, it's a little difficult to see, but you can see these double hoops, they're splitting open. And that was another fascinating discovery that we had through this test program. So as I mentioned, a lot of the bars either buckled or fractured, or some of them actually ended up staying relatively straight. The ones that stayed straight were on the east and west ends, not in the direction of loading as you would expect. But we had a few bars that buckled, and many of the bars that buckled and fractured. Now, it's one thing to see or say that yes, bars buckled and bars fractured, but it's another to see how they buckled. And this is, again, another example of using these technologies. I was able to get a 3D point cloud of the damaged column. And you can clearly see in some of these where the bars buckled not only in the outward direction as you would normally expect, but you get some bars that buckled along the circumference. So like this one, you can see it buckled not outward, pushing against the hoop. The confinement kept the bars from pushing out. And some of them, like this one, actually pushed the hoops and created like a kink inside the hoop and where it wasn't circular anymore. So these point cloud models, even though they weren't done during the test, this is all post-mortem, you can still get valuable information regarding the behavior of these bars. Another experiment we did was an exterior column of a multi-column bridge bent. So we took an existing bridge that is in California, Massachusetts Avenue overcrossing, and we did a 3/4 scale model of this bridge. We were looking at an exterior column in a multi-column bent because of the added complexity of having such a test. When you have an exterior column, you have variable axial load during the loading cycles. So you can go from anywhere between practically no axial load on the column and up to 12% is what we saw. 12% F prime CAG on the column. So we modeled this and built a 3/4 scale specimen and reinforced it again entirely with grade 80 reinforcement to see the behavior and determine if we can replace the grade 60 in the code, in the current design codes, with grade 80 in the plastic hinge region of these columns extending into bent cap connections. And we ran this test. Now, this was an interesting test. I'm not going to get into too many of the details of how we developed the hinge system at the base of this column, but you can read about that in the published work. Again, another short video. You can see that because we have variable axial load in the cycles, you get more damage on the interior face of the column versus the exterior face. This is showing you the interior face, and this video here shows the exterior. When you're pushing and pulling, you get higher axial loads on the interior side. You get a lot more damage, and you can see these bars buckling, some fractured over here. And once again, what we see in this video was some bars buckle not outward, they buckle along the circumference of the column. So we did another point cloud model of this so we can, effectively study the damaged specimen and get more information about the fracture mechanism of these bars. So once again, during this experiment, I didn't have LiDAR scanners or any of that stuff, so I had to make do with what I had at the time. The next set of tests I did was more on the material localized behavior of reinforcing steel, grade 80 reinforcement under sustained cyclic loading, where we have a bar that's embedded on both ends. So we created a sort of a fixed connection on both ends, and we did repeated push and pull cycles on this bar. Put it in tension, put it in compression, tension, compression, to buckle, enough compression to buckle it. And we wanted to see how these bars behave after sustained cycles. And we expect that during the compression cycles in the buckled shape, you get some minor little cracks developing, compression cracks developing along the ribs of the bars. So we wanted to gauge the behavior of grade 80 large diameter bars in these types of sustained loading situations. So we did a series of tests on number 14 grade 80 bars. Now we repeated these tests with these newly developed number 14 grade 80 bars that have a smoother transition for the ribs. So the top image here shows the typical ASTM A706 grade 80 reinforcement, where your ribs are defined per the code and how they have to be. These are the newly developed bars that we were trying to see how sensitive they are to these large cycle deformations, where these ribs are a little smoother, the transition. So we expect that because this transition is smoother, the development of those little compressive cracks will be a little delayed. And sure enough, it was, and the outcome of this has been taken up by the industry, and they will be producing these bars with a more smooth transition for the ribs. So just some details about how we ran this. We had a clip gauge system to measure the strains along the plastic hinge region as we expected, and we instrumented the bars heavily with strain gauges along the entire gauge length, just to get some local information about the buckled shape. But since we don't know how these bars will buckle based off of the previous test that I showed, some might buckle in different directions. You might expect that they have a weak axis and a strong axis, but it's not necessarily always true in which direction the bars will buckle. Another application of the technologies that we used post-test. So these are pictures of the fracture surface, the bars that break based off of those compression cracks. So a compression crack will develop in the compressed cycle in the buckled shape, and that crack will propagate and go through the entire bar, and that's when the bar will fail. So we created 3D point cloud models of all of these fractured bars so we can get detailed information on the surface and how these cracks propagate, because looking at the fractured surface, you can see where the crack started and where it goes. And in this video here, you can see there's a crack that didn't lead to failure right here, another crack on the other side that propagated through and actually led to ultimate failure. So those were the experiments that I did. Some available technologies that could be used and would be very useful for future testing are DIC, GPS systems, etc. So I ran a series of tests using DIC, visual image correlation, and just as a proof of concept for myself. Now, these tests that I ran, we don't have the capability at the time, and as far as I know, still don't. We're developing them to get higher frame rate DIC work. So what we had to do, we were capable of doing 2 frames per second, which is not good enough for dynamic tests. But we just did a tensile test on a number 14 bar, instrumented with strain gauges as well, and we compared the results that we got from the DIC. And they matched up very nicely. You can see the Poisson's ratio where it starts at close to 0.3, goes to about 0.5. And you get some very nice correlation between the data obtained from the visual image correlation and the data obtained from the strain gauges. Another application of this would be a useful practical application of DIC that should be extended is you can see the propagation of the strain along the bar. So here you can see the Luder bands develop along the bar where the deformations go from being elastic deformations to plastic. It doesn't happen all at once. You see the progression going through. And in this short video, you will see that it's going to start progressing and coming down. You can see the progression of the strains. So this would be very useful on larger scale tests. Now, this is a very small scale, very localized, but if you can see the damage progression on a large test as it's happening, that would be very, very useful. Another example, this set of slides was provided by Dr. Yehuda Bach. It's regarding the GNSS, or Global Navigation Satellite System, effectively GPS systems. We've done some work at UCSD, and some experiments have used this technology at the Shake Table at LH Post, and an ongoing project is happening right now at Scripps Institute of Oceanography. So GNSS provides millimeter level precision, really high precision measurements of dynamic permanent displacements in 3 dimensions. And if you have a cluster of these GPS antenna, you can actually get orientation data as well, which is very helpful. The GPS systems, I'm going to call them GPS because in the US it's GPS. We can go from 10 hertz to 50 hertz sampling rate. And they've been deployed, as I said, at some experiments at the UCSD Shake Table and at the UCSD Geisel Library. And that's an ongoing experiment, which I'll touch on in a little bit. So if we combine these GPS sensors with accelerometers, we can get a full spectrum of displacement all the way through the spectrum with high frequencies, which would be very useful. And obviously we used these GPS data to georeference UAV and LiDAR measurements so we can have precise models of the environment. And that can be helpful to develop models for the test specimen and also for structural health monitoring. One example project is the first project that took place at LH Post back in 2006. This was a 7-story reinforced concrete wall structure that was built at the LH Post. It was instrumented with GPS antennas, and they were co-located with accelerometers. So this is the GPS antenna, and on each antenna we had MEMS-based accelerometers also attached. And there was a GPS antenna reference on the platen itself to see the displacements, to measure the displacements on the platen, and a reference GPS antenna away from the platen just to keep as a reference. The next project that used this technology was the BNCS 5-story building that was fully outfitted with all the non-structural and structural components. They had a working elevator, there was stairs, there was furniture, there was a hospital suite in one of the floors. in this project, the SIO, in conjunction with UCSD, outfitted this building with GPS sensors as well. And you can see in this quick little video where you can see the test and you see the roof displacements here and the foundation displacements measured by the GPS. I'm going to skip the video in a little bit, but just to show some of the progression you can see here. The GPS system here was also ran in 50 hours. The next project was a partially precast concrete 4-story structure that was also tested at LH Post. Once again, this was outfitted with 6 GPS receivers. There were 6 of them were on the structure itself. 1 was outside as a reference point. There were 4 on the corners of the roof. There was 1 at the roof center and at the northwest corner of the foundation. And again, these were GPS sensors with the MEMS-based accelerometers and an epicenter accelerometer from the SIO. The other project that has made use of this technology was the cold-formed steel frame building with Professor Tara Hutchinson. The left image here shows the geometric model of the test building with UAV imaging. This was captured using a drone. This is after the test had completed, where there was the fire test already done, so you can see the fire damage on this floor. The right image shows the post-test. You can see the residual drift at the roof of 1.4%. That's after a 6% drift from the 3rd floor, where the fire test had caused extensive damage. Now, using the GPS systems, you can use the data from the GPS systems to get better models from the UAV as well. A project that's currently ongoing is the use of GPS systems at the Geisel Library. Now, this started in 2017, and the idea is to develop a nonlinear finite element model to predict the measured response over time of how this structure is behaving over the course of years, so you can monitor it and assess any kind of damage that might occur. So what they are doing right now is outfitting the Geisel library with GPS sensors and putting a sensor far away, a few hundred meters away from the library itself as a reference point. And using accelerometers that are being embedded on the structure itself, they're monitoring the long-term health of this building. So this slide here shows the motions, the 3-dimensional motions of GPS on the roof of the library with respect to a reference point a few hundred meters away. The precision of these hourly readings, this is for the north, the east, and the vertical displacements. And if you look along time, this is over 3 years of time, you can see the residual displacements are about 1.5 to 2 millimeters in each direction, and very, very little in the up and down. Now, using accelerometers, you can measure the noise, the ambient noise on the structure that's not detectable by GPS. GPS can detect the larger displacements, but not necessarily the noise. So that would be a very useful application of incorporating accelerometers with GPS systems. Now, looking to the future, as the satellite constellations increase and are more available, now in the US, it's GPS systems, the Russian GLONASS, European Galileo, Chinese, I don't know how to pronounce it, Baidu, I don't know. They're collectively called the Global Navigation Satellite Systems, GNSS. As these increase, we're going to get better sampling rates and more robust measurements of displacement and orientation, and we can get more precise georeferencing data for UAVs and LiDAR imagery. Now, as I mentioned earlier, integrating this data, the GNSS data, with accelerometers through Kalman filters, it can provide us a full spectrum of precise displacements and velocities. And it can provide us with an integrative tool for structural health applications, such as structural health monitoring. Now, to save some time, I'm going to go through these a little faster, but another technology that has been used is LiDAR, as you've heard in other presentations already. But we can use LiDAR to get very detailed point cloud analysis of full-scale buildings during earthquakes and fire tests. And this is the cold form steel building example that was talked about earlier. You can extract a lot of information from the test. You can look at the baseline model. So you do a flyby model and you get a baseline for the building. And then you do a final model after, the tests have been completed. And you can compare the two with georeferenced information, and you can get very detailed residual displacements from that. So this slide here shows the baseline model of the building using LiDAR. Now you can see at the top, you're missing some information, and that's primarily due to the high level of reflections at the time when these scans were made. And here you see the final post-test scans that were done, and you can see the deformed shape of the structure as well. So using these two sets of data, you can actually find a lot of information regarding the displacements of the structure and the behavior of the structure. Comparing the data, you see that we validate the LiDAR data with the data that we had from the GPS sensor. In this case, it's the pink dot. And the green triangles here show the linear pots or potentiometers that were used. Now, you can, up to a certain height, you can have a reference point where you can measure off displacements using instruments that are available. So it only goes up so high. But you can see that the LiDAR data is very, very accurate in reproducing the residual displacements in each floor. The next cool tool that could be used for tests, at large scale tests at the shake table, is UAVs, as we've already mentioned as well. So this is an example showing the UAV, using a UAV to track the motion of the building during the shaking. What is of interest here is the absolute translational rotational displacement histories of the building roof. You have to make some assumptions, such as, the roof behaves as a rigid body. There's no differential deformations there. You have to assume that there's negligible vertical displacements in the roof for this test, because it was a 1D test. And we have some information that's available to us. We have the roof displacements that were measured by the GPS system. We have the video that was taken with the drones from the top, and we have the LiDAR point cloud data that was geo-referenced from earlier. So again, as I mentioned, there was some GPS receivers put up here, and that's where the measured GPS data comes from. So to use this motion tracking technology, you have a procedure that needs to be followed. So you take the UAV-based video, you need to correct for the lens distortion. And after you've corrected for the lens distortion, you need to correct the UAV drift and orientation at both the ground level and the roof level. You can get the exact, you can extract the UAV location and the orientation. And once you've completed those initial preliminary steps, then you get into the actual motion tracking, where you have to do some edge detection and line fitting and some processing work and pixel tracking to reconstruct the time history of the displacement of the structure. I'm very short on time, so I'm going to kind of blaze through this, but this is a short little video showing the results of this motion tracking using UAVs, where you have the green and the pink colors showing the reference and the UAV displacement. Validating these results, you can validate these time histories using the video that you obtained, the GPS system. Now you have the unfiltered video in red and the filtered video in blue, and you can see that as you process the information, you can get remarkably accurate displacement and time histories. Now, just quickly going over the equipment and sensors that we have available at LH Post, well, at LH Post 6, once we reopen, we are building our new data acquisition system. It's gonna consist of 12 nodes, and what you see here is just one node. Each node has 64 channels, and they're capable of sampling 25,000 samples per second at 24 bits, simultaneous sampling per channel. 25,000 samples per second is way more than what's typically needed, but we have that capability. So if you have a test coming up and you have special sensors that require really high sampling rates, we are capable of that. We have plenty of instrumentation available on site, all the way from accelerometers to linear displacement transducers, string potentiometers, load jacks, load cells, and pressure transducers. All of this is available to the researchers. We do not stock strain gauges. Those are consumables, so we ask the researchers to provide their own strain gauges for each test. But these reusable sensors, we have quite a few of them. We also have a GPS system on site available to use that can be operated at 50 hertz. We have 3 of these receivers that I've showed that have been used on some tests, and we can use on future tests as well. We also have a whole suite of camera systems and imaging equipment available. We have some drones. We have the DJI Phantom 4 Pro. We have a lot of GoPro cameras, and we're constantly updating and getting newer cameras with better features. They have a synchronized remote system where we can synchronize all their videos as well. And we also have a bunch of IP cameras and different types of cameras that are also time synchronized with your test activity. And we are capable of live streaming with almost zero latency all your tests to either social media or your private websites, or just share with any other interested partners. And with that, I am going to conclude. I'm sorry I'm a little bit over time. If you have any questions, please put them in the Q&A and we will answer them in the Q&A section. Thank you.
Thank you very much, Kurosh, for your great presentation. So the next presentation will be given by Professor Paolo Calvi from the University of Washington, and he will talk about an example project with the RAPID. So Paolo, the floor is yours. I think you are still muted, Paolo. Still muted. Now I think should.
I think you should hear me now.
Yeah. Yeah.
Okay.
Great.
Okay. Great. Yeah. Sorry about that. Not sure why. Okay. So let me share my screen. All right.
Yeah, we can see it well.
Okay, great.
Yep.
Good morning, everyone. And first of all, thank you for having me. It's great to be able to present some of the work that we have been doing over the past year as part of this National Science Foundation support project titled Japan-US Collaboration on the Seismic Performance of Reinforced Concrete Structures. So what I'm going to do is I'm going to give a brief introduction and project overview, and then talk about the equipment we used in this project, go a little bit over the data collection and data processing, and then show some examples of the type of data that we have been able to extract so far. So this project fits in the context of an broad area of damage-based post-earthquake assessment of reinforced concrete buildings. And there is a lot we could talk about right here. I don't want to go off that tangent. I want to keep it focused on what we have done in this project specifically. So one thing I will say is that with respect to assessing buildings kind of in a post-earthquake environment, there are three main steps that are very important, and those are data collection, data processing, and data interpretation. The focus of this project was on data collection in a controlled environment, and I will explain what that means, and then on data processing. So those are the two focus of this project in the context of post-earthquake assessment of reinforced concrete buildings. So the test that was ongoing at the time, that was about a year ago, was December last year, was the perfect opportunity for us to collect data in a controlled environment. So a full-scale 3-story reinforced concrete building was being tested at the E-Defense facility as part of the Tokyo Metropolitan Resilience Project. And so this was the perfect opportunity for us to just show up and take measurements as this building underwent a series of ground motions. So the main project activities and objectives here were to first deploy state-of-the-art equipment available through the NHERI Rapid facility. And what we did is we decided to focus on LiDAR technology. And I'll go over a little bit. I will go over the equipment that we deployed later. Obviously collect experimental data mainly in the form of point clouds, while gaining at the same time reconnaissance experience in a controlled environment. So it's great that we were able to do this with a shake table test, because everything is known in a test like that. The input is known, the building is fully known. All the uncertainties that sometimes arise as we show up after a real earthquake were eliminated here. And so it was great to be able to not only know everything, but also to be able to compare the data, the results that we obtain with the equipment that we use to collect data with more traditional instrumentation. And finally, to process the data collected, and this is sort of an ongoing work. We're still in the data processing phase. But anyways, the goal was to process the data collected and evaluate the data quality in the context of extracting relevant performance features. So the ultimate goal that we have in mind, obviously, is to be able to perform assessment of buildings. And so all the data we collect needs to serve that purpose. And so what we wanted to figure out was if we could extract features such as global displacements, interstory drifts, crack maps, crack locations, spalling, anything that could give us indications on the status of the building. There were a lot of people involved in this project, obviously, a lot of Japanese colleagues that I'm not going to list here. It's impossible to do that. What I'm showing here is just the US research team that was sort of supported through this NSF grant. It was a group from the University of Washington, with myself serving as the PI for this project, Professor Lowe's serving as the co-PI, Tatsuhiko Sweet working on this project as a graduate student, and Tyson Tuma is an undergraduate student that worked on the post-processing with us over the past few months. Then we had members of the Rapid facility joining the project, specifically Professor Berman, and he's the facility operations director, Jacqueline Pelletier, facility operations specialist, and Andrew Lida as the Rapid facility operations engineer. And then we also had a team joining us from the University of Nevada, Reno. They were mostly interested in monitoring the building and tracking dynamically and statically what was happening throughout the shaking, using digital image correlation. This is a system that they specifically developed at the University of Nevada, Reno. The PI of that for that was Professor Mustafa and the graduate student on the project was Luna. I'm gonna say her last name wrong. Yeah, I don't know how to. I prefer not to say that. I don't want to say it wrong. So just a few words on the specimen that was tested. It was a full-scale 3-story reinforced concrete moment frame. It was designed according to the Japanese code to be a building of importance. It was 10.4 meters tall, that is 34 feet. And what this was not that important to us. What the Japanese team was trying to investigate here, we're really interested in the data collection and data processing, but they were investigating both the impact and behavior of structural and non-structural elements. And so we collected data pertaining to both systems. And well, just as a note, the ground motion was applied only one direction, specifically in the east-west direction, and I'll give you a reference system in a second. So in addition to all the structural components, obviously, such as foundation slab, floor slabs, beams, and columns, there were a series of secondary structural components, or sometimes considered non-structural components, such as standing walls, hanging walls, seismic slits, and wing walls. Those were interesting components that the Japanese team were interested in assessing. And then we also had non-structural elements throughout the building, such as suspended ceilings inside at some of the floors. We had tiles on the outside of the building, and there were windows and pipes on the roof as well. So we have data pertaining to all those components as well. And here's a view of the specimen before testing. And that's us, just to give a sense of scale. And also we were there setting up one of our scanners. So the building underwent a series of shaking. So there was only one ground motion that was considered throughout the week. It was tested over 3 days. And so always the same ground motion, but kind of ramping intensity. The first day, the building was tested under a 20% amplitude of the design earthquake, and then a second shaking at full design amplitude. So we were able to take baseline scans before sort of the shaking that the building underwent on day 1. And then we were allowed near and on the table, essentially at the beginning and at the end of each day. So in between, there were also some white noise testing going on to kind of characterize dynamically the building. We were not allowed on the table for those, but we have recordings for pretty much every test that matters in a way. So day 1, baseline, and then after 100% design earthquake shaking. Day 2, before testing and after testing, the amplitude was 150% of design earthquake. And day 3, they pushed it up to 160% when they decided to kind of stop the test. And so we were able to scan after that as well. So a little bit on equipment. I know you have heard about equipment available through the RAPID facility before from Professor Berman, so I'll go somewhat quicker. I'm sure you have seen this before. So we decided to focus on LiDAR measurements, LiDAR technology. We deployed 2 scanners and 1 total station. We mostly used as a reference. So we deployed the Leica RTC 360, which is a 3D laser scanner. Characteristics of the scanner are high portability. It's hard to get a sense of scale from the photo, but this is pretty much as big as a big camera and pretty light to carry around. This laser scanner can take fast 3D scanners and create point clouds with points every 3 millimeters, and takes at the same time panoramic images. And it's equipped with semi-automatic point cloud registration. can scan the entire surrounding 360 degrees in about 5 minutes, including unwanted points, meaning not only the specimen, really the scan goes on 360 degrees. So the whole facility was actually scanned. The resolution is a little lower than the other laser that we brought with us, the P50, but still pretty good to get global displacements and such. And obviously the fact that the whole surrounding is scanned results in very large data sets. The second laser we brought with us was the P50, which is a long-range scanner with high resolution. It creates a point cloud with points every 0.8 millimeters. And at the same time can also provide low resolution scans. Essentially what we did was we used the high resolution scans on regions that we were most interested in and ran low resolution scans everywhere else. It's also equipped with dynamic capabilities if it's ran in this line scan mode that I will talk about later. So both static point clouds and dynamic capabilities using this line scan mode that I'll talk about later. The low resolution scan is as quick as the RTC 360, about 5 minutes. But if you want to go high resolution, which is what we did multiple times, it takes much longer. And that's why it's good to just use the high resolution capabilities on areas that are of higher interest, such as areas that are heavily cracked or where there is spalling going on or something like that. And finally, we brought the total station with us, which was believed to be the most accurate of the three and was used to essentially create the reference system that we used to register all the instruments together. I'll talk about registration later. So a little bit on data collection. We took a lot of scans because one of the goals of this project was really to learn how to do these things properly. And so we probably took, we tried to be very redundant and take more scans than we needed. We took about 80 scans with the RTC 360 after each before and after each test. We took, I'll show later, scans from multiple locations. With the P50, we took fewer scans because of the time that the P50 requires if you go high resolution. But we tried to really be efficient at recording with high resolution point clouds all the regions that were of high interest in our opinion. And with the total station, we took the location of multiple targets. I'll explain what that means later, from 3 locations around the facility, the defense facility. So this is an example of point cloud constructed using the P50. This is a low resolution point cloud using the P50. And just so you know, each point is tracked in the XYZ coordinate system. So we have the position of each point throughout the point cloud. We have the intensity of each point, and we have the RGB color values for each point. So those are 3 features that can be used in post-processing to extract data of interest. Just to give a sense of the amount of data that were collected here, this is just an example after test 3. So the 3rd day of testing, we took 11 scans using the P50. Where you see those little triangles is where we took the scans around the facility. The shake table and the specimen they are in the middle. And before cropping the data, meaning before just isolating the data that are relevant to us, we had more than 2 billion data points. And after cropping and focusing on the shake table and the specimen, we were left with about half of that. The reason being that the facility, so the points that we eliminated were the points taken at low resolution, whereas on the specimen and the shake table, we had a lot of high resolution scans. That's why it's only reduced by half. Here's the same thing with the RTC 360. You can see that in the time that it took us to complete 11 scans, high resolution with the PIP50, we're able to complete 81 setups after test 3 and collect about 9 billion data points. And again, after cropping, so eliminating the facility around and just focusing on the shake table and the specimen, we were left with about a third of that. So this is the kind of, to give a sense of the amount of data that is collected after each scan. And here's an example, a low resolution point cloud example taken from the RTC 360 with locations where the scans were taken from, indicated with those little triangles around the facility. Here, an example of a high resolution point cloud taken with the P50. So this point cloud has a point every 0.8 millimeters. And this just to show that once you have the point cloud, I don't know how well it's showing on screen on your end, but you should be able to see that there is a big crack and some spalling around the lower side of the balcony here, and the crack that propagates from the balcony down into the beam. So that's the type of data that you have available to you right after processing your scans, high resolution scans. And scans were taken from the outside as well as from the inside of the building. So this is an example of a scan from the inside. And again, here I wanted to just show that this really blows my mind every time I look at this. You can really clearly see cracks and exposed rebars and spalling. And if you look carefully, you can make out the shape of the aggregates inside they are exposed right there, which is great. So this is the type of data that you have access to from the high resolution P50 scans. Just a few words on targets. So a big, or perhaps the most challenging task of the whole process is the post-processing of the data, not so much the acquisition. And so it's important to be clever during the data acquisition phase of the project. And so what we did is we used a series of targets that we kind of spread around in the facility to have sort of a fixed absolute reference system, as well as on the shake table and on the specimen, so that we could track the position of those targets from different scans and also have an absolute position, assuming obviously that the facility doesn't move during shaking, create an absolute reference system using those targets and have all the instruments registered together in the same global reference systems. So here just a view of some of the targets attached to the shake table. So we have some magnetic targets attached, for example, down here, M1, and paper targets just glued to the specimen as well. And this is just the west direction. So the building was shaking sort of in the west-east direction. And here's another view of some of the targets we had on, I believe, the south face here. Now we have obviously the position of every point. That's part of the point cloud. So we don't necessarily need to track the position of the targets to figure out displacements or other data that's relevant to us. But having the targets gives us a good reference to track, as well as, like I said earlier, common points between different scans that are used to register all the different scans together. So here is a view. This kind of complicated drawing here shows what we did with the total station. So essentially we had, where you see the dashed red circles is where we took measurements from using the total station, and we tracked the position of all the targets we could see from those 3 locations. And so all this T with a number represents target attached to either the facility, so kind of the absolute reference system, or to the specimen. Specimen is the kind of the purple lines down here in the shake table. And so using measurements taken from those 3 locations using the total station, we were able to, well, on one end, kind of verify the measurements acquired with the other 2 lasers, but at the same time to kind of register everything together. One note I would make here is we didn't think about this at the time, but perhaps taking some measurements from the other side of the specimen would have been better. Not necessary. I mean, we can work everything out with these 3 locations we considered, but that's one thing we learned, that having measurements taken from the other side would have been better, because we could see that way we could have seen targets on this side, the north side of the facility as well. And so once we have all our scans completed and all of our measurements taken with the total station, we can register, well, first of all the P50 scans with all the P50 scans and the RTC 360 scans all together, and then register everything in the reference system of the total station, which improves accuracy. And now everything is enforced to have the same coordinate system, which is much more convenient to work with in post-processing. So here's some example of the type of data that we have been able to extract so far. One thing, so again, the ultimate goal is to be able to extract features that are relevant with respect to performing the assessment of the building, meaning figuring out how badly damaged the building is after each shaking. So that's sort of the end goal. And so figuring out or being able to calculate global deformations and displacement, residual displacements, and so on, it's relevant in that respect. And so once you have your point clouds registered and everything is the same reference system, calculating displacements and deformations is actually pretty straightforward. It requires a lot of work, but it's just about tracking points throughout the different scans. And that can be done by taking a reference point on the point cloud and just tracking the displacement of that point, or tracking one of our targets that were attached to the building. So here's a simple example where the displacement of the structure was tracked by keeping track of the position of one of our targets. So you can see one of our targets, not very clear perhaps, but it's right here in the baseline scan. And here the photo below shows the target after one of the tests. And then we can overlap the 2 scans. And because everything is the same reference system, we can actually track the movement of that target from one shaking to the next and extract residual displacements in this case. And we can do that for every floor, for every point in 3D as well, obviously. And again, this is just another example of us tracking the position of our targets attached to the south face of the specimen throughout tests. So that was about global displacements and interstory drift, mostly residual, obviously, because you take kind of shots after and before each test. So statics measurement. And the nice thing about, let me take a step back, the nice thing about tracking displacements is that you get very accurate results even from the low resolution scans. So the RTC 360 provides good estimates of global displacements. However, when we dive into the damage detection, this is really the part of the work that's still ongoing. We're trying to really spend our good amount of time here because it's really important to us with the ultimate goal in mind. So basically performing crack identification and quantification possibly in point clouds. This obviously requires high resolution scans. So we're using the P50 results in this phase here. And everything is still done manually But obviously one of our goals is to automate this process moving forward. But right now what we've been doing is basically go through the point cloud we have, the 3D point cloud, and identify regions that present damage, such as spalling, exposed rebars, or evident cracks. And then go in and try to see if we can use filters to identify those cracks and also to quantify cracks or spalling or other damage features, not necessarily just cracks. But cracks are a very important indicator of damage in reinforced concrete structures, obviously. Just a reminder that the point cloud, every point includes information about the XYZ coordinate. We have information about intensity and RGB values. So we can use combinations of those to figure out damage features. And so here is an example of damage detection techniques that can be used to kind of track cracks and damage in general from point clouds. In very big cracks, we have seen that we can actually go in and measure, physically measure, like manually, crack widths and crack lengths and so on, just like we would do in person manually during an inspection. That's not as easily done with small cracks, but things that can be done are, for example, fitting a surface and computing the distances. So use the Z coordinate, which is one of the information we have, use the Z coordinate to identify valleys on the surface and identify cracks as a consequence. And what we've been doing is we've been trying to identify cracks and then compare what we see with the information that were collected on site by the Japanese team, which basically collected crack and damage information by hands using crack gauges and such. And so far we have seen a very good match between our data and theirs. Here's an example of the sophistication of the data that can be extracted from these point clouds. This shows the photos of course, the photo on the left shows the 3D point cloud of the whole building. What we see on the right is a portion of a slab taken from the first floor of the building. And what's great in my opinion here is that we had scans taken from the ground floor, so from below the slab, and scans taken from above the slab. And then when you kind of register everything together, these two scans are kind of patched together, and it's great that we can detect the crack at the bottom of the slab. We can see how deep it goes into the slab, and we can relate that same crack to the crack that we see from the top. And so it becomes the same crack that we can track in our point cloud, which is something that's extremely difficult to do if we're just acquiring crack information by hands. And then obviously we can isolate a crack. This is the crack that was just showing on that slab, isolated and made into a plane. And then we can adapt 2D image filtering techniques to 3D point clouds. And like I said, use either just the distance information of each point or the intensity, the RGB, or combinations of those to identify the crack and possibly to measure important features such as crack width, crack orientations, and the like. So this is really what we're working on right now. And yeah, this is just an example of the type of filtering that we have been working on lately. So our future goals for this phase, which is for this part that is the damage detection and kind of damage quantification, include obviously developing techniques or adapting existing techniques to detect finer cracks. So far, we have spent time looking at evident big cracks or big chunks of spalled concrete. We want to make the process more automated, which would speed up the process significantly. And then long term, obviously, we want to be able to use the damage information collected to perform assessment of the building or to put together models of the building. The last thing I want to touch on is the dynamic mode that the P50 scanner can be used to kind of extract information dynamically about a building during shaking. Obviously not practical in the field necessarily, but it's a great tool in a lab. So what we did was we set up the lines, the P50 next to the table during shaking, where we're not allowed near the table at all. But what the P50 can do is, if it's pointed towards the building, it can essentially record the profile of a column during shaking. So essentially the P50 shoots a line 360 degrees. So as usual, we acquire data that we don't need about the facility as well. But also that can be kind of cleaned up in post-processing. So what the laser does, it kind of tracks one single line at 50 hertz. And so here it probably gives a better idea of what I'm trying to explain. With the scanner position, where you see the dashed yellow circle here, the dashed red line is the line that's tracked at 50 hertz throughout shaking. And so this is cleaned up. So same view, just without the building. And so what we have done is, during not all of them, but most of the tests, we have run the scanner in this mode and tracked the position of that column that we were shooting at as the shaking went on. And so you can see here an example of the type of data that's collected. You have a single line before the shaking is started, during the 20% shaking, little displacement. So the red line is always the reference, and the green or yellow lines are essentially represent the column of the building that we're monitoring, moving back and forth. Obviously big displacements, because the data is including the displacement of the shake table as well. But once you get that, in post-processing, you can isolate the displacement of the building by subtracting the displacement of the shake table and focus on points lumped at each floor, so that you can get displacements in time for each floor, and from that calculate floor displacements, interstory drifts, and so on throughout the shaking, so versus time. And from that also potentially characterize the building dynamically. So this is the type of results that can be extracted from running the P50 in line scan mode. This is the displacement in time of second floor, third floor, and roof level. And from the displacement recorded at the very end, when the shaking stops, the interstory residual displacement can be calculated easily. And so we're pretty happy where we stand with this. We have compared the results of this line scan mode with the results acquired using more traditional technology by the Japanese team. Just one note on that. See, this is a great thing about having the point clouds of the building. If you don't remember exactly how something was done or set up, you can always go back and look at the point clouds. So here's a view of one of our point clouds where we can see how the displacement was being measured by the Japanese team. They had essentially posts attached to the floors, one sticking out from the floor and one sticking down from the roof, or from the upper floor. And then they had lasers kind of shooting from one post to the other, and that measured the interstory displacement in time. And here
Paolo,
is
I'm sorry to interrupt. I just wanted to remind you of the time.
Yeah, I'm done. Thank you. Yeah, and so here's just a comparison between displacement in time obtained using the P50 and using the lasers in the mode that I just showed. So with this was the last thing I wanted to touch on. Just wanted to thank all the Japanese colleagues that worked on the project, in particular Professor Nishitani, Professor Kuzunoki, and Dr. Yu, staff at the eDefense, in particular Nakamura-san, and obviously the National Science Foundation for supporting the project. And with this, this was the conclusion of my talk. And I believe if you have questions, we'll talk about that later.
Thank you very much, Paulo, for your excellent presentation.
Thank you.
So in the interest of time, maybe now we're going to go to the last portion. And so this will be a panelist presentation. We're going to have 3 panelists, Professor Paulo Calvi, whom you just heard, Professor Jonathan Hubler from Villanova University, and Professor Erika Fisher from Oregon State University. I think they are all here. Good morning. And so the idea here is to have these young faculty members and researchers to talk about new ideas for future research, new approaches, new tools, new technologies, and so on. And we hope to have they each will make a short presentation, I think 5 minutes, and then we will have a live discussion with them, the panelists and the attendees. And I think, Kurosh, am I right that the attendees will be able to unmute themselves and speak freely, I think?
Yes, yeah. So we will enable everyone's option to unmute and engage in a conversation. And at that point, we can answer any questions in the Q&A as well.
Great. And we also have one question for Kurosh here, but we'll keep it for this when we'll have the open discussion. So who is going to start? You guys are free. Erika or Paulo or Jonathan?
Erika, why don't you go ahead and start?
All right. All right, here we go. Okay, can you see my screen? Okay.
Yep.
All right. So I'm Erika Fisher. I'm an assistant professor at Oregon State University. And I'm going to talk today about data collection that we did after a wildfire. So after the 2018 Camp Fire, we used the Rapid facility equipment to go down to Paradise and collect some data. These are my co-PIs, Sarah Hamida from Stony Brook University and Hussam Mahmoud at Colorado State University. So the goals of our project were to look at schools and hospitals. We wanted to look at what the damage was to these 2 facilities within the town of Paradise, but we also wanted to look at what wildfire mitigation occurred at these facilities and what worked and what didn't work. And then lastly, we were looking at the role these institutions played in the recovery of the town of Paradise. So because of that last part, we had Sarah Hamida on the proposal, who's a urban planner, social scientist at Stony Brook University, and we actually received funding through the Humans, Disasters, and the Built Environment. So not through the ECI JOY program. And so, there's a lot of knowns and unknowns after wildfires. So these pictures are from the town of Paradise. So you show up and what's damaged is a pile of rubble and sometimes very hard to distinguish, but also there are no sensors throughout a community for wildfires. So it's like showing up to a post-earthquake scenario and not having access to any ground motions. Or so it creates some problems when you're trying to piece together and pull together this puzzle of what happened because you don't have any quantifiable measurements of what the hazard was. So we could know the weather the weather conditions and the post-fire conditions of the buildings, but very often we actually don't have documented mitigation techniques because you don't necessarily have to file that with the building code officials in your town. We don't have ember exposure, heater exposure, or energy released by the fire. These last 3 are really how we're categorizing the hazard. So we're trying to piece together a lot of information with a lot of unknowns, especially when we're just looking at these piles of rubble on the ground. So we used a number of different equipment, and then we used interviews. So I'm going to talk today a lot about how our interviews actually helped us gather a lot of that information. And I would strongly suggest that you include a social scientist on your team when you're doing these post-earthquake or post-hurricane or post-hazard reconnaissance, because it does allow you to flesh out the data set that you're collecting. For us, we use these more traditional engineering approaches, taking pictures, obviously, using LiDAR to actually scan some of the structures so that we could do finite element analysis back at home, and try to figure out what the hazard was in the building that caused the deformations we were capturing through the LiDAR. We took a lot of drone imagery also to get kind of aerial outside shots of the buildings, but also to look at mitigation in forests and look at burn severity from mitigated and unmitigated forests. But this only really got us halfway there in our goals and objectives. We could summarize the damage and we can identify commonalities in damage, but we really couldn't do or tackle the rest of these objectives. For that, we really needed our interviews to know what the pre-fire conditions of the buildings were. None of the tax records told us when these buildings were built. This helped us know what mitigation techniques were taking place, grants that were applied for, and again, that role of these institutions within the recovery. So I'll wrap up quite quickly with these lessons learned. So the first lesson is really that we needed all four to capture our goals, to actually accomplish the goal of the grant and get that holistic picture of what happened in Paradise. We actually went down 5 times to Paradise, but the first time we actually went down and did a scoping mission. And for anyone who's looking to do post-hazard reconnaissance, I would strongly suggest this. It is really hard to figure out what happened when you're going through mainstream media. The mainstream media makes it seem like everything is rubble. When you get down there, you realize what is actually standing still. And we went down, it was just me and my grad student. We went down for 2 days. We worked really hard those 2 days to visit all of the sites. And then when the rapid team came down with us the second time and the full project team came down with us, we actually had a plan. We had a schedule. We knew exactly what buildings and what areas we were going to scan, where we were going to use what equipment. We talked again with the rapid facility about what we saw. They were able to calibrate what equipment we should bring down. It was just really helpful. Just so you know, like, you're paying for equipment by the day, and you're paying the rapid facility people by the day. So the less days that you can use them, the more money you have in your project to do other things. So we actually listened to a lot of the survivors' stories during our interviews. This was really cathartic for them, but also it helped us build trust with the community and with these people for them to open up and help us with our research and help us, find the dates of the construction of certain buildings, get us drawings when we needed them. We presented our data back to the town every single time that we went down there. For those of you thinking about doing post-hazard assessments, I would strongly recommend going to the Converge network and listening to their ethical behaviors. It's really actually quite helpful. We're taking a lot from the community when we go into these communities and do this type of work. So it's nice to give back to them and inform them of what we're finding from their community. I know Paula said this, but trust the PIs at these NHERI facilities. They are the experts on their equipment. So I called Jeff and his team before I even talked to the program manager. He was able to tell me about what he knows about anyone else going into the field, what types of equipment I should probably be using. And it helped me with my discussion with the program manager for a rapid proposal. I wrote a career proposal this summer and wrote in the University of Florida facility. I did the same thing, contacted them immediately. A lot of times they will help you write the proposal, the section that you're using their facility for, and they will review your proposal. And so trust them, they are way more experienced than you are, and they are way more, they are so much more better and have so much more knowledge about the equipment. And then I know Paolo mentioned this as well, but data processing should be a task in your research methodology. If you don't want to process LiDAR data, then you need to include a different co-PI to do that for you. Or you need to put money into your budget to send your student up to UW and sit in their awesome office and work with the great team up there to process it. I did not do that. And so it created a lot of delays in getting that data. So think about it as the faster you get that process data, the faster you can start doing some work with it and publish your awesome papers and get your work out there. So this was co-funded with the Natural Hazard Center, and these are all my co-PIs and students and everyone else. I am way over time, so I'm really sorry.
Erica, thank you. That was great. Okay, Jonathan.
Yep. All right, let me just share here. All right, so good afternoon, everyone. I hope you're enjoying the workshop. I know I've sat in on a few sessions and it's been quite interesting. I'm going to talk a little bit about a rapid grant and project that I worked on for the evaluation of pre and post blast liquefaction soil and site parameters. And I'm Jonathan Hubler. I'm an assistant professor at Villanova University. So this project occurred in December 2019. So this time last year, we were in beautiful New Zealand. And for the project, we were looking at doing blast liquefaction testing in the Christchurch area. It was an area that had been subject to significant liquefaction during the Canterbury earthquake sequence. So it was right along the Avon River. So it actually used to be a place where there were houses that actually had to be knocked down following the earthquakes. There was 2 blast locations at the site. So one was treated with a soil improvement technique, and then one was just the natural native soils at the site. And so the goal of our project was to measure different soil and site parameters using a lot of different equipment from the RAPID facility. And we wanted to do this before and then immediately following, and then a little bit further following the liquefaction occurrence at the site. So the equipment that we utilize from the RAPID facility, we use the ATOM MASW setup for shear wave velocity measurements. We use the PANDA instrumented dynamic cone penetrometer. We use 3D terrestrial laser scanning, and this was completed by Mike Olson and some of his students at Oregon State University. And then we also took 3 seismometers. So we traveled from Philadelphia all the way to New Zealand with 7 cases, which the RAPID facility, they were helpful in helping us to figure out what we actually needed in terms of paperwork to get through borders and things like that. Definitely think about baggage fees when you are traveling internationally with this much equipment. It can be a bit of a sticker shock. But yeah, so this was all the equipment. They shipped it to us about a week early. So we were able to get the equipment in Villanova, try it out, make sure everything was working. We were comfortable, do any troubleshooting before we headed to New Zealand. Here's a picture of the ATOM system from the RAPID facility. So this is a wireless MASW setup. You can do active and passive testing. So each of those little individual yellow boxes, the atoms, they collect data and you can load that data back onto a computer via Wi-Fi or plugging them in at a later time. The battery life is something like 70 hours. So you can take this in the field and do testing all day. So this was the setup that we used. We did active testing at the site within the blast areas. We had different seismometers set up so that we could determine site period before and after the blast testing. So we had 3 of these, and we kind of positioned them at different locations around the site. These are pretty easy to set up, and you can, let them kind of sit in the ground, bury them, and collect data for an hour or 2, and then load that back on the computer later. And then the Panda instrumented DCP, you can see here that this can be operated by one person. It has a tablet. You can see the soil profile. This is some results from the site where they had done a cone penetration test prior to the tests that we did. And the Panda, which is very portable, we did these tests probably in about 45 minutes to about 4 meters depth. And we got really good agreement with the CPT, which would have been difficult to get on site. And then the laser scanning, you can see here the setup for that on the left, and then on the right, you see the results. So this again was put together by Mike Olson from Oregon State. And what you're seeing is at the one blast location, that's a profile of the settlement following liquefaction. So in the middle of the blast circle, you get the greatest amount of settlement, and then it decreases as you move outward. And you can see all of the different instruments that were tagged at the site. So there's more instruments than I've ever seen at a project like this. So I just want to acknowledge some of my collaborators. Kyle Rollins from BYU also had a grant to do this project. And then Liam Witherspoon from Auckland was involved in a lot of this, Mike Olson. And I talked with Joe a lot in preparation of this grant. And then of course the Rapid staff, I was emailing them from the field, getting information and things like that. So they've been great to work with.
Okay, guys, thank you so much, the 3 of you, for kind of really interesting applications, very different applications, really intrigued. So Karush, I think you were going to moderate this.
Yes, thank you. Thank you very much, everyone, for your great presentations. Some really cool topics. So right now I'm giving everyone the option to unmute themselves and engage in discussion with us. But before we start that off, we have a question in the Q&A that I'd like to answer, and we can just go right ahead and engage in discussions among ourselves. So the question was actually for me. Considering the vast equipment in your research, do you think that it is practical for general evaluation of the building right after a major earthquake? And considering the existed bonding models of steel and concrete, what makes your pull-out tests novel? Are they determined? Are the determined rupture surfaces different from pre-assumed determined surfaces considerably? So for my tests, I think for general evaluation of buildings right after major earthquakes, the tools I used were probably not very efficient, but that's because I didn't have the proper tools. For me, the point clouds that I got were not in the scope of my project. That was me doing that predominantly for posterity and to investigate things that I personally wasn't looking into, but in the future I could look into and others can look into. My experience has been projects are pretty expensive if you want to run a test. Construction costs, material, labor, everything. So it's in my eyes, it's useful to have these data available, so researchers don't necessarily have to run another test just to look at one thing. If there's enough of data available, then they can look through, let's say, my data and see if they can use some of those point clouds that I have and obtain new information or use it for their own research purposes. So I think using proper tools from Rapid could actually be very advantageous. And you've seen quite a few examples of those tools like LiDAR and UAVs being used to evaluate buildings right after earthquakes. So my answer, I guess, to make a short story long is my tools, what I did, I don't think is very practical for, evaluating buildings right after earthquakes, but there are tools that Rapid does have available, and there's many tools available that are very effective, and I would highly recommend them. Regarding the bond models that I showed in my presentation, we've had some very elaborate bond models for both monotonic testing and cyclic behavior from Eligahausen back in 1983, I want to say. And they've been worked on by many researchers. And the most recent that I'm aware of is Murcia del So in 2013, I want to say, who did quite a bit of work and updated the bond model. Through my tests, we didn't have too many data points. I only had 4 tests. So we can't conclusively come up with many findings. What I did see, and hopefully more tests in the future can actually improve on this, but what I did see was there was a little bit of a marginal increase in the bond strength when we went to higher strength concrete. And there was a little bit of fluctuation between the same concrete using the same bar in 2 different kinds of concrete, or so 5 KSI concrete and 8 KSI concrete, but I can't definitively say what that change is attributed to without having more tests. But generally speaking, I would say the bond stress relationship was a bit stiffer in higher strength concrete. And I can elaborate if you'd like to contact me, after this workshop. We can get into a full discussion with my findings. And lastly, the fracture surfaces, they were close to being in line with what was expected. I saw that the fracture surface wasn't necessarily symmetric. The cone had different angles on different sides, but they all were roughly in the 25-degree angle to about 35-degree angle sides with all 4 specimens. So that was that was one of the key things that we did observe. But again, I can go into more detail if you'd like. Just contact me, separately, and we can discuss. So I hope that answers your question. So with that, I'd like to open up the floor for open discussion. So everyone has the ability right now to unmute themselves, and our panelists and all the attendees, we can just talk.
Sometimes maybe we need a little kickoff. Okay, so I'm happy to do that. So I have a few questions, I think, for our panelists, and I'm hopeful that each of these will lead to some sort of interesting further discussion, but we can see how it goes. I'm really interested to know what we could be, as facilities, both UCSD and the Rapid facility. I think we're both super interested in the next kind of iterations of measurement technologies. And so I'd like to hear from each of you. Each of your projects was so different. I'd like to know kind of from each one, if you could have collected the perfect data, the data that explains your research question most directly, what would that have been? And, and then maybe we could think about how do we get there? But first off, I think we need to identify what would that data have been? In no order, just jump in when you take a minute, think about it.
Yeah, I can start. So I guess the perfect data for me would have been you know, immediately following the blast, if I was able to get data, you know, they kind of have to go in and give you the all clear that it's okay to walk and that all the charges went off. But that's actually a lot quicker than I thought it was, based on talking with some people. But it was pretty fast that we were able to get back in. But you know, setting up the equipment, and you know, you kind of are competing with other people too, because they have to do their stuff, and you don't want to disrupt their data collection. So I think being able to leave the sensors at the blast site would have been perfect, so that you could measure the pore pressures, you know, as they elevate from liquefaction, and then as they start to dissipate, you know, in that window, right, you know, as liquefaction occurs, and then following. So it took a little time. We were still pretty quick. I think the MESW setup, we were able to get measurements about 30 minutes afterwards. But maybe having some type of blast resistant sensors, which might be a little bit of overkill, but that would be, I guess, the perfect data, I think, for me.
To build off of blast, because fires kind of come after that, I think, I mean, gosh, if there were sensors in a community, like during the wildfire, if there were temperature sensors or heat flood sensors, that really would have been wonderful for us. I think where we struggled most is more on the processing side. So we can collect all of the data that we want, but we want to know what the out of plane deformations were, or local buckling deformations of very thin steel members. We want to be able to measure flange thicknesses and everything of members when there aren't existing drawings, so that we can go and basically what we did is we created a fine element model of the building and then subjected it to a ton of different fires to try to get the same deformed shape, and then said, this is what could possibly have happened. So in these communities, you know, we're seeing more and more that it's the older buildings that are damaged. You know, no modern buildings are going to be really damaged from the hazards that we're looking at. So when we are looking at these older buildings, a lot of the times we're not going to have drawings, which as structural engineers is like, you know, the golden ticket. So you know, that we can actually pull that information from the data that we're already collecting. So really it was on the processing side that we were struggling. And, you know, this is the biggest challenge, right, of today, of using all this great data. We've really jumped in our technology from the tape measure to LiDAR, and the processing side hasn't caught up yet. So if anyone on this call is looking for, you know, you know, what is, like, you know, the next proposal, like, definitely look into being able to process LiDAR data quickly and get that information.
Yeah, to go along with what you just said, Erica, with processing data, that's a big deal. I mean, hopefully somebody can figure out how to get through all this data in a reasonable time frame. Maybe machine learning or something. I don't really know, but I did want to ask you. So you said that when you went for your reconnaissance missions after the fire, there was no information available, or very, very limited information available. How do you mitigate that? Would it be, you know, cities or localities embedding sensors throughout the city, or are we talking on a building level to put some sensors that are always connected and we just kind of monitor through time? Or is that something that's unrealistic at this point because it's too expensive, or what are we dealing with here?
Yeah, it's a good question. You know, being able to actually quantify the hazard. There's no common language right now with quantifying a wildfire that impacts a community. So there is common language in quantifying the wildfire. It's burn severity. It's calculated through satellite imagery, but it's calculated on a 30 meter by 30 meter scale, which is a bit coarse when we're talking about a community. So we there's, how do you compare one wildfire to the next? There's no consistent language and there's no state of the practice for doing that. So it's quite difficult. So yeah, the temperature in fire is like equivalent to like the magnitude in an earthquake. It's like really helpful to communicate to the public, but it doesn't really tell you much about the hazard. So it's like really like we want to know what the energy is that's released. So we want to know like heat flux. That's really helpful for fire people in the fire field. So there are heat flux sensors. They require a lot of electricity though. So so I don't know. I mean, it would be great if there were some sensors throughout a community that could inform us, and I think it would just totally change the field in the way that we can talk about the hazard.
Great, thanks.
Yeah, it's really interesting. Attendees now. I'll just keep posing questions. So I think one of the barriers to deploying kind of instrumentation like you guys have used either in the field or in the lab, and specifically, if you think about a project where you might be doing something on LH Post 6, where either using the soil box or doing some sort of foundation test perhaps, or on a full structural system. I think one of the barriers to using all this new technology is really kind of, and yeah, I think you guys all touched on this a little bit, is the comfort level of the PIs running the other science portions of the project, right? Who might be, doing this test to investigate aspects of liquefaction or, the behavior of a reinforced concrete moment frame. And it's really challenging to ramp up and think about data acquisition on using these new tools and new concepts. So as kind of, three kind of young, exciting faculty with the future all in front of you and stuff, what is kind of required for you to feel comfortable, and do you feel like it's necessary to partner? And do you think that will change over time as you envision the next 10, 15 years, 20 years of your careers?
So Jeff, can I say one thing here? Can you hear me?
Yeah.
Oh,
Yeah.
okay. Yeah. So I think there are steps, going back to my experience at least, there are steps that are relatively simple steps that could be undertaken to make life easier for PIs that want to use the rapid equipment in a full-scale shake table setting, such as the UCSD lab. For instance, one thing we spent some time thinking about, and maybe we didn't even get right, was the positioning of the targets around the lab. That's something that could be relatively easily done at UCSD, sort of integrating the current facility with simple positioning of targets around the facility, maybe talking with the rapid staff for optimal positioning and efficiency of measurements and whatnot, and even maybe figuring out locations around the lab from which taking the measurements makes sense. So we had to go through a lot of guesswork in Japan and not really knowing what we were doing, to be honest, and so just taking more scans probably than we needed to, not necessarily from the best positions, positioning the targets where we thought made sense, not necessarily getting the best positions right. And so I think these are things that could be done at UCSD and kind of make the lab more readily available to sort of deploy rapid equipment and get scans, for instance, or basically what we did in Japan, but with the lab at UCSD already set up to work with the rapid equipment. So that's something that, I don't know if that answers your questions directly, but that's something I thought it would sort of help PIs that want to use this equipment during shake table tests.
Hello, regarding your comment,
yeah.
So UCSD, the outdoor shake table. So your outside target would be like the safety towers that we have, and have dots on them, and
something like that. Yeah. So you could have, I guess the tower would serve that purpose. Maybe kind of trace locations from which taking scans kind of around the shake table makes sense to take
on the ground. On the ground.
On the ground, yeah, on the ground. On the ground, something like that. That would make life easier for a PI that just needs to sort of deploy the equipment and then just show up, and there are kind of locations tracked down on the floor or targets already attached to reference points. I think that would be helpful.
That's a great suggestion and very easily achieved. We need monuments around the shake table facility, right? Survey monuments to tie into.
Right.
I think that's fantastic.
Jeff, this is Tara. Joel already thought about this, and he put this gigantic reaction mass there for you. So it's beautiful. Actually, you can attach to this. We've done that in the past with the aerial view UAV. It's just a function of thinking about the scale of your target, the black-white target. We have a little experience that we could share with people when they're thinking about doing that. How high up you're going to be is important, clearly, as the resolution decreases with the camera sensor that you have and the like. But thank you to Joel for putting that beautiful reaction mass there for us.
Yeah, that's great. That'd make a great monument for sure.
I think though what Tara brings up a good point of not being afraid to ask. I think that as we're writing these proposals as younger faculty, don't be afraid of your own limits. No one is all-knowing. You'll ask a lot of questions, but it's good to ask these questions so that these facilities know where your lack of expertise is, and if they might suggest a co-PI to you, or they might help you out in these areas that you're don't have a lot of knowledge in, and then you'll go through that project and you'll learn and you'll be more knowledgeable for the next one. I just have been so thankful for the expertise at these NHERI facilities, of the PIs that are running them, and just their willingness to help out, to make our proposals successful. It's sometimes I'm like, do you want to be a co-PI on this? You've helped me quite a bit. So it's but I just think that there's take advantage of that knowledge, and there's absolutely no way, if you've never used LiDAR before, that you're going to know where to place targets. So by asking the questions, you're gaining the knowledge and you're learning. And so I would say just don't be afraid to expose your lack of expertise in a certain area, but explore kind of new ways to use the equipment.
Yeah, it's a good point, Erica. And actually, I think what you gain from that, the more people you talk to, everyone's encountered some practical limits. And you mentioned LiDAR, and as an example, the first time we were setting up LiDAR, we completely forgot about a whole bunch of occlusions that would be there. You need that direct field of view, and we captured the data, and then we did some tests, and then we went back and went, oh my gosh, you could see this when you walked from this angle or that angle. Oh, man, we really wanted a different view. And so had we taken a little bit, to be honest, we all have to make those decisions, and we make them quickly. And so sometimes we've learned them really hard way, unfortunately. So sharing those experiences, I think, is all in the spirit of the NHERI infrastructure. Actually, it's not for us that we're supporting the facility for the community. It's kind of a thankless situation. We want to see the community succeed.
So related to this target, oh, sorry, go ahead, Corey.
Go ahead, it's okay. If you have
go ahead.
Sure. So we have a question that popped up in the Q&A. Have anyone used LiDAR to scan dynamics of trees under some load? Oh, can't hear you, sorry.
Well, I'm this is Joe. I'm sorry, just leaving a EU meeting that took place since early this morning. So I'm joining the workshop a little bit late today. I'm going to try to answer that with a quick no, but I'm going to answer that because we are developing a scheme now to support actually an FHWA project to image rockfall in process. And so we're working on dynamic monitoring. And we've done this already. I think I mentioned yesterday at UCSD, we're working with Scripps at the Wave Tank in Northern California, the Kelly Slater surf tank. And we've also done this in Duck, North Carolina, imaging waves in a 2-dimensional profile. And so the work we're doing now is trying to do this 3-dimensionally during the whole rockfall process. So very high rate scanning. So there's really no reason why you couldn't apply that same idea to trees. And one of our scanners in particular, our Leica scanner, we have control of the operating system. So we write code to operate it. So we can tell it, it's not a standard option, but we can tell it to scan this box at this rate for this long. And I think one thing you'd be really interesting to see is just the way, the aerodynamic resistance of leaves would fold over and potentially change in wind and so forth. So no, but I think we could work on that. And I think that also is one of the things we spend a lot of our times doing, is trying to figure out ways to use our existing equipment portfolio to answer and to capture these unusual data streams, not just from natural hazard kind of post-disaster settings, but we do a lot of work in just the natural hazard space, the kind of non-disaster space as well. So imaging trees is something that's absolutely in the realm of possibility.
Erica was probably pretty excited about that because it's a precursor to wildfire, I guess, right? And wildfire spread.
So I wanted to just give Jonathan one chance. It looked like you were about to unmute and respond to the previous.
Yeah, I was just going to say, obviously, I agreed with what had been said about recognizing what you don't know and partnering with people that have an expertise. But just thinking about that a little differently in terms of field work too is the amount of planning, right? You need to kind of go down that checklist and think about everything, because inevitably things are going to go wrong in the field, and you're going to need, your brain power and critical thinking skills to figure out those issues. So if you can plan for, everything else and make sure you're talking to the right people so that you have all that stuff planned out, there's going to be things that you don't know. I mean, even in my project in New Zealand, I had used different MESW setups previously, but the one from the Rapid just, it had its own kind of idiosyncrasies that made it, different than what I had used before and kind of changed some things. So just things like that, then you got to be fixing those in the field, not figuring out where you're, spacing the sensors or things. If you can get all that done, it's going to be a big help.
Another question for you guys. How would you prioritize the need for more money in terms of, if you could have more money, would you buy more advanced, more sophisticated equipment, maybe for higher resolution data? or for developing methodologies, techniques to, to process this gigantic amount of data, or more money to develop the theory further or develop, better models? How would you comment on that?
I'll take a quick shot, and I'll let anyone else from, at least from our facility and then UCSD could respond on this as well. I think that we have our instruments, the state of the art in instrumentation hasn't changed all that much since we acquired our portfolio, which was only about 4 years ago. So that hasn't changed too much, but we are really, we have a lot of data, and it's worthwhile to know that about every day of data collection in the field on average has about 2 to 3 days of post-processing. So I think that we would probably prefer to invest in making the post-processing more efficient and to develop workflows to streamline that. That's really kind of what we're about. We're trying to let you concentrate on your science and trying to support your science. And we've been doing that with the tools, but we'd like to also do that after you collect that data. So I think that's where that's kind of my sense of where where we might want to go.
Thank you, Joe. Yeah.
Panelists, where should we put our money in our renewal?
I mean, I agree with Joe in like the processing side. I hate to like harp on that, but again, I do think that as at least on the structural side, I know the geotech has been using drones and LiDAR for way longer. So, but it seems like we made a massive leap in technology, and we don't necessarily know what to do with all this data. And I think it's like a cool thing to do. It's like it's definitely a trend. It's like putting sustainability in your proposal. But it's now, the problem is like, we don't know what to do with it. So I think if there was more knowledge or speed in the processing side to make the data more accessible to universities that don't have like LiDAR experts or anything like that, I think that we could see more universities around the world and around the country using that data a little bit more. So you're kind of lowering that barrier to entry. We could probably like bring that data into the classrooms more. We could do a lot more with it. I'm like really excited for the future, knowing that we have this massive repository of data on potentially doing something with it. I just think that we need to get it in a more accessible form.
Yeah, thanks. I appreciate that.
I did want to ask one thing from the Rapid folks. Have you started or are considering at all, making use of the LiDAR sensors that are now commonplace, like on phones? Or is that something that's not precise enough or worth effort to actually look into?
We've definitely been having conversations about what we can do with it. I think right now the precision accuracy is it's good for capturing kind of architectural maybe level notion of a room. Oh, should I move my couch over here? But for detecting cracks in plaster and things like that, it's you still need a better piece of equipment than your iPhone. But I think though those technology, as that stuff becomes more ubiquitous, I think it does lower the barrier to entry and gets people a little bit more comfortable. I think back to like, coding, right? Coding for structural engineers, what an evolution it's been since I've been a faculty member for 15 years. When I started the student coding, it was like, no, I can't do this, the students, right? Just revolting. And now actually everyone's doing really, it's been a pretty dramatic shift in the students understanding and how comfortable everyone is in coding. And I think that's part of, as these technologies kind of make it into mainstream life, doing it at high resolution and high precision necessary for the types of things we want to do. It's just taking what they already kind of know a little bit about and just getting better with it. So I think it's a positive. I don't think it's useful for us as a facility, except, it's useful in the same way that maybe, we had some really fast LiDAR systems when we first started up this thing called the structure sensor, and you could just walk in and swing it around and, it'd pull a room together really quick. But it doesn't really, it's not precise. It's not giving you measurements.
Yeah, I'll just add to that we have these systems. We've purchased those iPhones and iPads just to experiment with them a little bit. We do have a lower threshold below which the data is of just such poor quality and inconsistent that that it's just really not ready for research use. And I think that that LiDAR sensor, although it's really cool and it can kind of georeference a couple things for your photos, it's not really ready for research. But you really don't need to use it because we have a portfolio of 3 laser scanners that are 2 pounds with a very lightweight tripod, our BLK 360s, that are single button operations. You push the button on the top, it'll do a 360 degree scan. It will do a thermal image. It will do a high resolution 360 image as well. So it can all be fused. So it really is not, so we have that, and there's could be nothing easier than turning on the power and pushing the button and telling it to scan. And again, doing the post-processing of that and registering it is a little bit more work. But we have easy ways to acquire that. But this kind of came up with our drone LiDAR system because there were very early drone LiDAR systems that used a device known as the Ballantine Puck that we looked at, and was just the data quality was so low. And while it was novel and it was a low barrier to entry and it was light to carry on a drone, we just felt that we couldn't stand behind that data. And so we eventually opted for, we said we wouldn't consider this and found a system that improved, which is not to say that in 2 to 3 years, there are not going to be higher quality sensors. But right now it's just really, we want to make sure that there's a lot of error and bias that is built into everyone using their own equipment and using lower end equipment. And one goal of our facility, one vision, is to take that out by using consistent, high quality equipment that also is easy to use, which was an important consideration for us when we were developing the portfolio. So I just don't think it's really needed at this time, and but it's not to say that won't change in the future.
Great, thank you. So I think with that, if there's no additional comments, we can conclude this open discussion session.
Yeah, thank you so much, Erica, Jonathan, Paulo. Thank you so much.
Yes. Thank you.
Yes, thank you very much. All right, so I guess now we are at the end of the workshop. And so I'd like to thank the speakers and for the excellent presentation, the panelists for their great performance. Thank for the attendees, for attending this 2-day workshop that jointly with the NHERI Center, with the NHERI Rapid Center. And we hope for the attendees that they were able to, that you guys were able to get the information that you came here to get. And you have met virtually at least members of the NHERI at UCSD team and the NHERI Rapid team. So please feel free to contact us if you have questions about, for example, the feasibility of your specimen in your next proposal or the testing procedures. We'd be happy to work with you on these things. We wish you the best for your research proposals and look forward to working with you on them. Because if you succeed, we also succeed. It's a two-way street. And I would like also to thank the individuals who have helped with the organization of this workshop. And I'd like to especially thank Kurosh Lotfizadeh and Tara Hutchinson from UCSD and I hope I pronounce his last name correctly, Michael Griot and Jack Peltier and Jeff Berman from University of Washington. And please do not forget to fill the survey that it's important for us, like we told you earlier today. I think Kurosh gave you the information, and I wish you all to stay safe and healthy in this difficult period, and a happy Christmas holidays. And I think that my colleague, Professor Wortman, wants to also say a few words.
Yes, thank you, Joe. I want to just begin by again thanking you and the whole team at UCSD for organizing this and for inviting our participation. We've been wanting to do this for a while. I regret that, of course, we're not doing this in person, but we'll be back there. But thank you for including this. I've enjoyed this. Since I had to attend another workshop this morning, my closing couple thoughts are really based on what happened in that workshop, but I think they're all pertinent here. Let's see if this works. The workshop was with an EU center in Pavia that many of you may know of. And I guess maybe I'll just sort of offer three quick closing things. For young investigators, we just had the reaction from the Europeans about how unique the US is in developing shared use resources. That's really not a traditional model that exists there for research infrastructure. So just recognize that this is everything we've talked about in terms of the Shake Table and the rapid resources are yours. I mean, we are here to support your work. And it's really unique that we have this kind of infrastructure. So please take advantage of it. I build a lot of my assistant professorship life on what was then the predecessor to NHERI, NEES resources, by doing centrifuge tests, using University of Texas equipment, among other instrumentation that was shared use. So please take advantage of it. Two is Joy Pauschke, and actually 3 program managers from CMMI were attending this workshop. And it is very clear that they believe that panels are receptive to proposals that take advantage of NSF investments in infrastructure, in research infrastructure. And panels like when they're combined. So if you're interested in preparing a proposal for UCSD, think about the ways you can draw in the other NHERI elements, because a couple projects were presented in the last meeting that did just that, not necessarily with UCSD, but with some of the other NHERI elements. So please take advantage of that. I think it will increase your chances of getting work supported. And I think maybe to Erica's point that she made a bit earlier, is that it also shows panels that you recognize this area or this acquisition of data as being important, but you don't have the expertise necessarily, but you don't need to, because you have found an NSF supported entity to help you collect that. And I think that puts them at ease, saying that they're working with a well-known group. And then maybe the last thing I'll say, this is a little bit more on the rapid side, but I think we've talked a lot about post-disaster reconnaissance and ways in which we can use the instrumentation to support laboratory experiments. But you should really think quite broadly as well. And as an example, I'll offer the COVID-19 Seattle Street View project on ways that you can use instrumentation for, to make an analogy about natural hazards or about disaster risk reduction. There's a lot of opportunities to creatively apply these instruments to kind of non-traditional problems and settings. So with that, I'll thank you all for attending. I really appreciate that you've been here for the last 2 days.
Thank you very much, Joe. And I forgot to mention one thing, since Dr. Joy Poshki could not present this morning, and not enough of you are interested in her presentation this afternoon, so she will not present at all today, but we can make available her presentation from last year. So we will do that. It's a PDF that is very instructive. And also, I want to remind you of the office hours this afternoon if you have specific question for either the Rapid or for you, NHERI at UCSD. Kurosh, any other things that we may have forgotten or?
No, thank you very much. I will send a follow-up email to everyone for the survey with a link that you can, go and access our survey. That would greatly help us out if you give us your honest feedback. And just to remind everybody, it is 100% anonymous. So please speak your mind. Thank you very much.
Bye, everyone.
Okay.
Bye, everyone. Happy holidays.
Yeah, thank you, everyone.